Okay, shall we get started? Can everybody hear me in the back? You're good? And you can see also? It's good? Okay. Okay, are we having lectures in this room for the rest of the rest of the semester? Okay, yeah. So you know where to come on on Wednesdays. This is the place. I hope you guys like this room. I'm not sure if I like it yet, but we'll see. Okay. We're going to continue, as I promised you at some point, we were going to do multi-core cache management, more cache management. I told you there was a time when the biggest symposium in computer architecture, International Symposium on Computer Architecture, was jokingly called International Symposium on Cache Architecture. That's CA. It's not true, really, but because there are a lot of fascinating topics in architecture, but caches have been very successful, as you know. They're employed everywhere, not only in hardware and software, but also software. But we will talk about some specific issues in multi-core. Can you guys hear me well? Okay, yeah. There's no echo or anything. Please shout if there's some echo. But let's do a summary of last 2 weeks. We've covered a lot about memory interference and memory control, providing quality of service. How do you mitigate and control memory interference? And we looked at different approaches. These are all very fundamental approaches. You could apply them actually in any part of the system. We've focused on a specific part of the system, which is the memory, main memory system, right, if you remember. But also we've given some examples from the higher level side, how to do virtual machine scheduling, for example, on taking into account some of that interference that's happening in the nodes. So hopefully this is useful for you, regardless of which route you take in the future. And when I was out of town last week, Juan talked about programming heterogeneous systems, and we had a discussion session. Are those discussion sessions useful? Okay, good. It's good to have more of them, less of them? No? Okay. So today we'll talk about shared cache management, but I'll get back to this more or less of them in a little bit, and making caching more effective. But before that, let's take a broader view of what we've done so far. We're actually beyond half of the semester, believe it or not. And we're not going to be able to cover everything I envisioned that we will cover. So you're going to miss out on a lot of fascinating topics in architecture, but I prioritize them such that the more fascinating ones come earlier, hopefully. So we had 14 lectures, all cutting edge yet fundamental topics. And let's take a look at them quickly so that it refreshes your mind. If you can see this, which you cannot, I think. I don't know why you cannot, but it's coming. It came. Now I cannot see it. That seems to be a problem. Okay, we've covered a lot of fundamentals, memory hierarchy, cache management, main memory. So these are all cutting edge and fundamental topics, actually. Emerging memory technologies, GPUs, branch prediction, control flow, memory interference, as we've discussed just now. So we're right now on the 15th lecture, I think. And I'll go back to this. Okay. And you've done 2 labs. I hope you guys are enjoying the labs. Are they good? It may be challenging, but my target was really 5, but we'll see if we get to 5 this semester. Maybe difficult. We may end up at 4. Okay, we have done 3 homeworks, and there will be more. Homeworks are mainly for your benefit. I mean, in the end, a grade doesn't matter in general, I think, but for homeworks especially, this is mainly to prepare you to understand everything, as I said earlier. And hopefully many readings. Are you guys enjoying the readings? Yeah, so. Some people are definitely, yes, that's good. Yeah, please do the readings. You'll learn most, I think, if you do the readings, especially if you want to do advanced stuff in computer architecture, whatever that stuff means. It could be research, development, ... Those readings will help you. And everything will help you in the long run, I think. Okay, so this is a good place to ask for your feedback. I don't want to use this lecture for feedback, but feel free to email me directly. And if you use my Gmail address, it's better, actually. That way I can categorize things much more easily. Interfaces matter, whatever people think. If you have a really good interface that you're used to, that's much better. That dominates everything, actually. User interface, for example, is really important today in how we interact with computers. Okay, so I'm always interested in any type of feedback you have about the course. Feel free to email. If you want to do it anonymous, we'll put an anonymous survey also, but there's no reason to be anonymous, I think. If I don't agree with your feedback, that will just not get implemented, right? And it's as plain as that. But But I usually try to take into account the feedback. And usually the problem is there's conflicting feedback, right? Some people think the course is too easy. Some people think the course is too hard. That happens always. But I think it's good to get your feedback and suggestions for better learning on your part. So if you can say, oh, I would learn better if you had more labs, for example, and less lectures. That's always good, right? But that's always conflicting also. I wish we had a really heterogeneous course where we can customize everything to every single person. That's really what's happening in architecture today, right? You're really specializing. You're adding these specialized accelerators to customize for applications. If we could apply it to education also, that would be nice. But I don't know how to do that. If you have ideas, I'd love to learn. I guess you could have individual professors that are customized to you, but that's a bit hard to do also. Okay, any ideas you might have on any related topic? I'm very open to getting your feedback, so feel free to send it. And as I said, we will put an anonymous survey also. So if you want to provide the feedback that way, that's also fine. And this goes without saying, I think, but I'll say it, and we'll talk about that later in the course. If you want to do research or development or whatever you would like to do in any of the covered topics, in any topic in computer architecture, hardware, software interaction, and related areas like systems, data centers, for example, feel free to talk with me. We have if you want to do research, we have many projects and a great environment to perform top-notch research. That's really important, I think, in research. You really need to be in a great environment to do something breakthrough, and ETH is a good place for that, for sure. So please talk with me, with the other TAs, who are actually my researchers, so they know some of the projects, but I have the bigger picture, of course. And you can do that email, in person, WhatsApp, if you figure out my phone number, which is not that hard. Actually, it's on the web somewhere, I think. Okay, so feel free to do that, or you can ask me. That's easier than getting it from the web. But please feel free to talk with me about this. And if you're interested in like jobs in this field, for example, or internships, I'd be happy to help with that also. Because sometimes, actually, computer architecture is interesting because sometimes it's hard to get into being a computer architect because it requires a lot of experience usually. You need to do an internship usually, for example, to be a computer architect at a big company like Intel or Apple, for that matter. So if you're interested in this area, I'd be happy to guide you, give feedback, even if you're not interested in doing research. But if you're interested in both, I'd be happy to talk. Okay? Okay, any questions? How many people are interested in jobs in this area? Architecture. Okay. Some people don't know. Okay, yeah, that's good. That's a lot of people. Yeah, even if you're not interested, I think there's a lot that you can take. You can apply a lot of these to other areas too. Okay, so let's jump into the topic of today's lecture, multi-core caching issues. So what changes in multi-core? This is a broad overview slide. I won't go through this in a lot more detail, but we're going to cover a lot of these actually as we go through today's lecture. Basically, the big difference in multi-core versus a single core is you get a lot more pressure on the memory or cache hierarchy, as we've seen in memory interference. Right? You get even more pressure on the caches actually, especially on shared caches that are shared by many, many cores. And if you have a multi-threaded engine inside the multi-core, multi-threading is another topic that I would like to cover if you have time. But you've seen fine-grained multi-threading, for example. You can have, in GPUs, you can have hundreds of threads that are sharing the cache. So GPU is a very good example of a multi-core engine. It's a different kind of multi-core, but it's really multi-core in the end. So you get a lot more pressure on the memory and cache hierarchy, so cache efficiency becomes a lot more important. And also, you have a choice again, right? Do you make the caches private? Do you make them shared across the core? So we're going to talk about that. And we're going to talk about in-between approaches that a lot of processors are today taking. What is that in-between? Providing fairness and quality of service. So you know about this already from the main memory perspective, but this is an issue in caches also. How to handle shared data between cores. If you're sharing data between multiple threads, where does that stay? Or does that keep ping-ponging between different caches? How do you handle cache coherence? How do you organize and connect the caches? If you want a really large cache, do you distribute it across your chip? Or do you have a single location where the cache sits? If you distribute it across your chip, now the local components are faster to access, but remote components are slower to access. As a result, you have non-uniform cache access, right? And what do you cache where? When do you move the data blocks? So there's a huge design space that opens up when you have this distributed kind of caches. And interconnect is another thing that you need to design in that case. It's another topic that hopefully will come up. Although when I did the calculation, we have only 9 lecture slots left, actually. So we'll have to... There's interference that's happening for the lecture slots from all the exciting topics in architecture. We'll see. OK, so placement and insertion, we'll get back to this, actually. We'll look at some new techniques that people have developed in terms of identifying what is most profitable to insert into the cache, profitable depending on some end performance goal, right? And minimizing dead or useless blocks. Because if you put a useless block in your cache, you're not only affecting your own performance right now, but you're also affecting many, many other threads' performance if that cache is shared between threads. And replacement, we'll also talk about that. So cost of error, for example. We've already talked about memory-level parallelism, aware cache replacement. But in multi-core, it's not just about memory-level parallelism. It's not just about recency. It's about also how much interference you're causing to others, right? So this profitable definition becomes much harder. OK. So before I move into the real topic, I'll briefly foreshadow cache coherence. We're going to talk about that. And if we have a lab 5, it's going to be about cache coherence. It's going to be the hardest lab, I promise you. But maybe we'll make it optional. So it's not going to be as hard as a Verilog cache coherence lab. So it will be a C cache coherence lab, C level. If you do it at Verilog, you'll have a lot more harder issues, actually. But that's actually a lab that you will learn a lot. Unfortunately, we may not have time, so I'm not going to promise that. Maybe we'll put it up so that if you want, you can do it on your own. How many people are doing extra credit, by the way? Don't be shy if you're doing it. OK, I see no one. I think someone submitted it, so yeah, maybe not this lab's extra credit. OK, let's go back to the topic. Basically, the basic question in cache coherence is, if multiple processors cache the same block, how do they ensure they all see a consistent state? We're assuming private caches here. So you have this processor 1. And this is not a problem just in multi-core. This is a problem in multiprocessor system, right? Multiprocessor system with separate caches. So you have processor 1. It has a cache. Processor 2, it has a cache. There's some network, and there's some main memory. And processor 2 loads into R2X, which is in main memory. It gets 1,000 in its cache block. Processor 1 does the same load. It gets 1,000 in the cache block. That's good. Now they have private caches, and they have the same cache block inside their caches. Now I'm assuming a cache block is just a single word here. This is good because now they can read quite fast from this private caches, right? The problem happens when someone wants to write to this location. Let's say this processor 1 does this operation on R2. R2's value becomes 2,000, and it stores the result. It wants to store that result to memory location X. So memory location X gets updated by this processor, becomes 2,000. But that location is already cached in some other processor, right? Now you have a consistency problem. It's really a consistency problem. It's also called coherence. But these words are actually two different things in today's architecture. When we talk about consistency and coherence, you'll figure that out. But basically, the data is now not coherent between the two processors. This is really the up-to-date value, perhaps, depending on your programming model. So when this processor loads X again from the cache, it should not get 1,000, right? So how do you ensure that? Well, we're going to talk more about this, but just to foreshadow some things, whose responsibility should this be? That's one of the first questions, right? You can say that hardware does nothing. Hardware does the cache over here. Well, good luck with that, right? If this cache is not visible to the software, then this processor will definitely load 1,000. So can the programmer ensure coherence if caches are invisible to the software? I've already given you the answer, basically, no. So cache needs to be somehow visible to the programmer, which already complicates things, right? Before, we assume that caches are usually not visible. But now, for correctness, cache needs to be visible. So how do you make the cache visible? Well, I will go through this relatively quickly. You really need some more thinking to really understand the issues over here. But what if the instruction set architecture provided the following instruction? Flush local A. And this instruction flushes or invalidates the cache block containing address A from a processor's local cache. When does a programmer need to flush local and address? So here, let's go back. So assuming you don't want to load 1000 here, and the only thing you have as a programmer is a flush local instruction, you can flush a cache block from your cache locally, deterministically. Would that help? I'm not sure, right? Because you don't know when this processor is loading, storing to this location. So whenever someone else does a store, you need to figure out, so you need to do a flush local. That's kind of weird. How do you communicate between those threads? So maybe this is not a good abstraction, right? What if the ISA provides something else, flush global A? Basically, you flush or invalidate the cache block containing address A from all other processors' caches. When does the programmer need to flush global and address? So let's go back here in this example. Let's rewind. This processor is going to store to X. Maybe right before the store, it issues a flush global, right? Saying, I want to flush this block from all other processors' caches because I'm going to write to it. That may not be a terrible idea, right? Now, the problem is, how do you ensure that when you flush global, somebody else is not going to load it right after you flushed it? Right? There's a race condition over there. If somebody else loads it, and then you store to it, they still got the wrong value, 1000. So there is a race condition between when these instructions are executed. Okay, so it's difficult to actually give this abstraction to the programmer and make things work. In fact, one of my favorite examples, I don't know how that happened, but processors that have not provided cache coherence, at least in the general purpose domain, did not fare well. One of the really interesting examples is the Ibm Cell Processor. Do you guys know about the Cell Processor? It was at least the early processors in Sony PlayStation. And IBM designed it. It's actually the first heterogeneous multi-core engine. It's relatively well ahead of its time. It had this big processor they called the control processor, and it had these smaller processors that were synergistic processing units or something like that, and the primary processing unit. This control processor was able to send tasks to these synergistic processing units, of which there were 8, I think. So it was a 9-core multi-core, heterogeneous multi-core, which I intend to cover in the next lecture. But it didn't provide cache coherence. So it was the programmer's job to figure out how to ensure how to manage the caches. Basically, caches were completely software visible in that case. And this was very difficult to program. That's why it got stopped, actually, and it's not, it doesn't get continued, even though it has really good concepts, some other concepts. But lack of cache coherence was a problem over there. So if the hardware actually provides this cache coherence transparently to the programmer, now we simplify the programmer's or the software's job. And it could be simple, actually. It could be very similar to this flush global, except the hardware can guarantee that the race conditions will not happen, right? If the software does this flush global, then maybe after the flush global that's inserted over here, you get an interrupt, and this processor goes away. So your flush global is actually useless, right? If your thread is descheduled from here, then anybody can load the same cache block again. So you need to keep doing flush global. There are ways of actually getting around that potentially by moving to different programming models, but they actually rely on cache coherence also. Okay, so hardware, one idea, a very simple idea, could be to invalidate all other copies of a cache block when a processor writes to it. Right? It's very similar to flush global, as I said. But you can design the caches such that they're synchronized. So this is, again, it's a short foreshadowing. This is called Snoopy cache coherence, not to be confused with the Snoopy dog. But basically, caches observe each other's write and read operations. This assumes a shared bus interconnect, not necessarily always true. A simple protocol could look like this. Basically, a cache block can be in the valid or invalid state. If a processor, let's say, if it's in the invalid state, and if a processor reads the cache block, it sends out a bus read signal on the bus, and everybody else observes that bus read signal. And they do nothing in that bus read signal, in this protocol at least. And it becomes valid. And then if a processor writes to that cache block, it basically sends out a bus write signal and modifies the cache block. In this case, val can be modified or not modified. It doesn't matter in this case. But when some other processor sees a bus write signal, and if it has the cache block in the valid state, it transitions into invalid state. Basically, that's invalidating the cache block when you receive a bus write signal. So you broadcast the bus write signal when you actually write to a cache block, and everybody sees it, and everybody invalidates, and you can write to it. And if somebody else now needs to read or write, you can handle it in the protocol. Right? So in this case, actually, there are some assumptions. That's why you don't see the bus read signal as an input over here. This assumes that the cache is write through, which means that whenever you write to the cache, you also write to the memory, and that's instantaneous. That may not be a good assumption, but if you make it work, it works. And no write allocate. You don't allocate when you write to it. And these are the different actions. So whenever some other processor reads, it gets it from memory. It doesn't get from somebody else's cache. Does that make sense? So even this simple protocol is actually prone to a lot of race conditions. How do you make it work such that somebody else doesn't read it before actually things get invalidated, right? Okay, that's something we will talk about. And that's why the last lab, if it happens, is the hardest lab, actually. Okay, any questions? I've given you the simplest protocol. This is not implemented in existing processors. You don't want to do just these two states. What existing processors implement, actually, what is called the Meze Protocol, which we will discuss, which is actually the Illinois protocol, because it was first developed in Illinois by Janak Patel and Papa Marcos, his graduate student. Basically, they have 4 states over here, and they can enable exclusive access. So if a cache gets exclusive access to a cache block, they can do whatever they want to it without informing anybody else. So that's the key idea in the Meze protocol, actually. And you will see the benefit of it later on. Okay, let's move to that. That was a foreshadowing of the cache coherence problem. But that's important to discuss because it affects the design decisions over here as well. And it affects a lot of other things, which we may or may not discuss because there's not enough time. So there's one issue in caching in multi-core. Are the caches private or are the caches shared? This is true also for multiprocessors. If you have single processor, another processor, and these are in different chips, you can again have the same problem. But in that case, private caches may make more sense on the chip, right? Here on the chip, you have a choice. You have this L2 cache. Is it private or is it shared? Why am I not depicting the L1 cache? Well, L1 cache is very closely tied to the processor, right, itself. So you can also make that shared, but everything we've discussed so far says L1 cache is very tightly coupled to the pipeline, and the design decisions of the L1 caches are made mainly by the pipeline frequency, for example. So even L1 caches may be shared between different threads over here, but let's ignore that for now. So if you have a private cache, the cache belongs to a core. A shared block can be in multiple caches. If you have a shared cache, cache is shared by multiple cores. You don't have the replication problem for the shared block, and the coherence problem goes away. So if you have this cache, you don't need to keep these coherent because there is only one place where that block that is shared by these different cores can reside, right? So a shared cache has a big advantage to begin with. But it has disadvantages also. So capacity is another advantage, actually. You get high effective capacity if you have a shared cache. For example, if this core needs, if these are each 1 megabyte caches and this is a 4 megabyte cache, if this core needs 2 megabytes and everybody else needs only 0.1 megabytes, these caches are wasted, if you will, and this cache is thrashing. Whereas if you have shared cache, everybody would fit comfortably into the cache, right? So you enable dynamic partitioning of the available cache space. You don't have the fragmentation issue due to static partitioning that I just talked about. It's easier to maintain coherence, and shared data and locks don't ping-pong between caches. So if you have coherence over here, if this core writes to a location, it needs to invalidate all of the other caches, and with the Snoopy bus protocol, what happens, it sends an invalidation, and everybody invalidates. And then if this core wants to read that data, it reads it from this cache or the memory, depending on what is up to date. Now you have the ping-ponging issue, basically. This core writes, it invalidates everyone. This core reads, it gets the data, and it writes again, it invalidates everyone else. So the shared cache block ping-pongs between different caches. This happens a lot with contended locks, for example, which again we will talk about, Because if you're actually trying to get into a critical section, you need to read the lock and then write the lock such that no one gets into the critical section. And also shared data that's contended as well. But this issue goes away over here, right? You don't move the data. So you don't waste a lot of energy. That's one of the other benefits of shared caches. Now, of course, with everything, like everything else, it has this trade-off also has its disadvantages. Shared caches usually have slower access because they're bigger. Now, this is an optimization decision, of course, but you can tightly couple these private caches to the cores also. You can make this interconnect much more optimized. Whereas here, you really need some sort of interconnect, actually. And if you remember, you can bank the cache, for example, but then you need an interconnect such that all cores can access all banks. Right? So it could be a crossbar, for example. So that complexity is not there. As a result, this can be much faster and much higher bandwidth potentially as well. Shared caches are slower access because of that. And one of the issues is inter-thread interference. Whenever you have shared resource, cores incur conflict misses due to other cores' accesses. They get misses due to inter-core interference. And some cores can destroy the hit rate of other cores. We're going to occupy ourselves a lot with this in this lecture. And again, you have the problem of guaranteeing a minimum level of service to each core is harder if you have a shared cache, right? Or fairness, even. Here, it's easy. You already have some minimum level of service or minimum level of cache capacity, at least. But here, you may not have that. OK, so free-for-all sharing, we've covered this in the context of memory system, but this refers to placement and replacement and insertion policies to be the same as a single-core system, usually LRU or pseudo-LRU, as we've discussed, or MLP or cache replacement, whatever you implement. It's not aware of the threads or applications that are sharing the cache. And an incoming block evicts a cache block regardless of which threads the block belongs to, right? Which thread or threads. Right? So it's not aware of this different cores in the cache. So this leads to similar problems like we've discussed. You get inefficient utilization of cache because LRU is actually not the best policy, and we will see that. And you should think about LRU, at least these recently used. We've actually spent a couple of lectures on cache management policies. And a cache-unfriendly application can destroy the performance of a cache-friendly application. I'll have to correct something on the slide. I know. I cannot stop myself, though. Something small, but inconsistency is not good. OK. OK, now not all applications benefit equally from the same amount of cache, right? Free-for-all might prioritize those that do not benefit. In fact, that may be the case. If you're streaming through memory, for example, you're allocating all of the cache blocks, and you may be occupying all of the cache, even though you're not getting any benefit from the cache. Whereas some other application that has good locality in the cache could have used that cache space much better, right? And as a result, you get reduced performance and reduced fairness. So we'll talk about how to handle shared caches. There are two things that we're going to talk about. One is controlled cache sharing. You don't want uncontrolled cache sharing. And there are two approaches I will discuss. One is designing shared caches, but controlling the amount of cache that's allocated to different cores. And when I say cores, you can think of hardware threads also, because this problem is actually much more general than just multi-core, even though I put it in the context of multi-core, because all of the systems that we have today are multi-core systems. OK, the second approach is to start with private caches, but spill or receive data from one cache to another. So these are two ends of the spectrum. You start either with private caches, you start either with shared caches. You make shared caching more controlled, maybe more partitionable. You move toward this direction. Or when you start with private caches, you make private caches more shared. You move toward this direction. And they both have advantages and disadvantages. Hopefully, some of those will become clear. And both are actually implemented in today's processors. And the second is more efficient cache utilization, because efficient cache utilization becomes extremely important in multi-core. So we'd like to minimize the wasted cache space by keeping out useless blocks. So if something is really useless and you can predict that it's useless, why do you even cache them? By keeping in cache blocks that have the maximum benefit and by minimizing redundant data. So we'll look at different approaches. So if all of your blocks are storing zeros, do you really want to do that? Right? Why don't you compress your data, for example, in the cache? Or why don't you deduplicate the data? We're not going to talk about deduplication, but that could be another potential thing. OK, so these are some examples for controlled cache sharing. I'm not going to cover all of them, but we're going to cover some of them. And these are some examples for efficient cache utilization. I think we should be able to cover all of them if you use the time wisely. Any questions so far? Let's move into controlled caching. Can people still see this? Yeah? I see a lot of light from there, so is it good? Okay, if it's good, that's fine. Okay, so we're going to talk about cache partitioning, basically, because if you want to control the sharing of a shared cache, you need to somehow decide to partition, right? If you want to close the things over there, if you don't see, let me know, or let Juan know. Yeah, maybe you want to take a look at that, because I cannot see it very well sometimes. But one is hardware-based cache partitioning. We're going to talk about software-based cache partitioning also. Again, like everything else, everything you can do in hardware, you can do in software also, but you run into trade-offs, right? We're going to start with hardware-based cache partitioning, because you can do very fine-grained partitioning at hardware level. And I'll start with an idea that has had a lot of impact, actually, in the last 10 years or so, which is called utility-based shared cache partitioning. The goal over here is to maximize system throughput. And the observation is similar to what I said. Not all threads or applications benefit equally from caching. And if you use simple LRU replacement, this is not good for system throughput. The idea is very simple. Allocate more cache space to applications that obtain the most benefit from more space. So the application that gets the higher marginal utility from an extra cache block, you allocate the cache block to that application. The key question is, how do you determine who gets more benefit? And how do you define benefits? Right. And the high-level idea actually can be applied to other shared resources as well. It's really a utility-based mechanism. And these are the papers that actually talked about this idea. This paper proposed an implementable mechanism, and this paper has an earlier mechanism that's a little bit difficult to implement. Okay, so we're going to define the marginal utility of a cache way, not even a block at the moment, because it turns out partitioning caches in terms of ways might be easier for reasons that you may see very soon. So utility is defined this way. Basically, this is the number of misses with A ways minus misses with B ways. Right? So if you reduce the if you go from, let's see, if you go from number of ways, initially you allocated A ways to a core. If you go to B ways if you allocate B ways to the core, you basically experience a reduction in misses, and that's the utility you get, going from A ways to B ways. These are cache ways. So let me give you one example over here. This is number of ways allocated from a 16-way set-associated 1 megabyte L2 cache for this application. As you can see, this application doesn't care, because it's streaming through memory. It has the same misses per 1,000 instructions, which is one way of expressing the miss rate. It's actually a better way than saying 90%. Right? Because 90% assumes that you have some accesses to the cache, but you don't know how many accesses or how big the impact of those accesses. If you say misses per 1,000 instructions, now you have an idea. So if this is 1,000, then every instruction is getting a cache miss. Right? If it's 1, then the 1 out of 1,000 instructions is experiencing an L3 cache miss, or L2 cache miss in this case. But if you look at this application, it's really insensitive to how many ways you allocate, at least in this configuration over here, low utility. But if you look at this other application, it's very sensitive, as you can see, and it keeps benefiting from the more cache you give it, the more it keeps benefiting, basically. So it has high utility out of the cache. So which one would you rather give the cache to? Well, clearly, in this case, the green application, right? In fact, you don't want to allocate anything to this application, perhaps, because it doesn't benefit. So that's the key idea. And these are actually real results from systems. You can actually replicate these on your systems also. And there's another application over here that has saturating utility. It turns out it fits into 5 ways in this case, almost 6 ways. And if you give it more cache, it's not going to have more benefit because it doesn't need more. So now, how do you allocate this cache space? Now it becomes more interesting, right? Okay, so motivation is basically what I showed you over here. LRU may actually give you a suboptimal allocation point. In this case, it's 2 other workloads. It may allocate a lot of cache to this application that's streaming after some point. Maybe it exploits some locality. But this application doesn't get allocated a lot. But a better way may be to stop allocating basically give this application only 3 ways, or whatever ways we see. I think this is 1, 2, 3, actually. And give this application the remaining ways, because this benefits more. This keeps benefiting from the additional ways you give to it. Make sense? The key question is, how do you find these points? It may not be that easy. So basically, we would like to improve performance by giving more cache to the application that benefits from more cache. And the idea is relatively simple. It requires some implementation challenges, of course. So we have 3 components. We want to monitor the utility each application is getting from the cache, from each extra way. These are called utility monitors. So for each core, you will have these. And we will feed these utility numbers to a partitioning algorithm that decides how to allocate different ways. How many ways do you allocate to each application? And, of course, you need to have a replacement support to enforce partitioning. Does that make sense? So we're going to do it at a way-based way level, because collecting information for the utility is easier if you look at different ways. Basically, the associativity will be our limiting factor in terms of how many ways we can allocate. Or that will be our partitioning granularity. So let's take a look at what these utility monitors are. So you'll remember some of these, basically. For each core, we're going to simulate the LRU policy using a separate tag store called auxiliary tag store. You remember this, right, from MLP, or cache replacement paper. Because in the main cache, we're going to follow a policy that partitions the cache. But we would like to be able to figure out what would be the utility of giving more ways to this application. So even though it doesn't get all the ways at this point, you'd like to be able to see the full picture. How do you estimate what would be the cache miss rate of an application if it were given 1 ways, 2 ways, 3 ways, 4 ways, 5 ways, 6 ways, ... But it's not given that at the moment. So you need to have a separate tag store over here. And we'd like to have hit counters in this auxiliary tag directory to count hits for each recency position. And we're going to take advantage of the fact that LRU is a stack algorithm. So for example, if you have 2 ways, if you have a 16-way cache, but if you want to figure out what would be the number of hits you get if you had only 2 ways, you can just look at the top 2 ways in LRU. You need to think about that a little bit. But it's really a stack algorithm. By definition, you keep inserting things in the most recently used position. So by looking at just the top 2 ways, you can get the number of hits you would get by allocating 2 ways. Now, if you want to see what happens if you allocated 3 ways to this application, you add H0, H1, H2, the hit counters that you dedicate to the 3 different ways. So let's take a look at what these hit counters are. Basically, in the auxiliary tag directory for each set, this is a 16-way cache. We have 16 hit counters, 1 for the MRU position, 1 for each position, and the last one for the LRU position. And for each application, you have an auxiliary tag directory, or each core, and you keep track of what is the hits you would get if you had the first way. What is the number of hits you would get if you had the second way also, ... Right. So let's take a look at an example over here. You have these counters at these different positions. This is 4-way in this case, but it's easily extensible. Whenever you get a hit to the MRU position, you increment the counter at position 0, which is MRU position. Whenever you get a hit in this position, second to MRU position, you increment that counter, and ... And it so happens that this is the hit counter values that you observe for an application at a given point in time, and you also know the number of misses, clearly. If no one hits, then you increment the number of misses. So you can actually draw this curve online while the program is running, is you have these hit counters per position, per LRU position. And this curve looks like this, basically. It basically transforms this data, translates this data to the number of misses over here, and the number of ways per set you allocate to this application. If you give only 1 ways, if you give only 4 ways, you're going to get 25 misses. You know that. If you give 1 more way, if you take away 1 more way, you're going to get 10 more misses. If you take away 1 more way, you're going to get 15 more misses. If you take away 1 more way, you're going to get 20 more misses. And clearly, if you don't give any cache, you're going to get all of the sum of this. That's the estimation rate. Okay. Does that make sense? Cool. So, of course, this is unrealistic. As you know, if you have an auxiliary tag store for each application, you have a problem because this is big and expensive. And we're going to use the same method that we introduced with MLP-aware cache replacement, which is dynamic set sampling. And if you remember, the idea is dedicate only a small number of sets for which to collect this information on. And it turns out 32 sets in a large cache is sufficient. You can read the paper for analytical bounds. And this was the idea of dynamic set sampling. You just dedicate 3 sets to collect this information and use that information to decide how many ways to allocate to an application. And the storage cost is relatively small. OK, so you know about this MLP-aware cache replacement. Let's go to the second component. Now that we have the hit counters, we have the utility of each cache array for each application, what do we do with it? Well, one way of designing the partitioning algorithm is this. Evaluate all possible partitions and select the best. If you have 2 cores, this may be easy, with A ways to core 1 and 16 minus A ways to core 2. This is the hit counters that you would have from the different utility monitors. And you basically look at all possible A values and select an A that maximizes the hits, number of hits. That could be one optimization point, right? You could, of course, have other optimization points, but this is relatively simple. And you can do partitioning once every n million cycles. I should really fix that to be n rather than 5 million, but the paper that I'm going to describe does it every 5 million cycles. So you could actually adapt to dynamic behavior by doing this periodically, right? OK. So hopefully that's simple. We're going to get back to that. So how do you enforce partitions? That's the third thing to do over here. And the idea over here is way partitioning. You need to complicate the cache a little bit. Each line needs to have some core ID bits to associate it with the core that has brought the cache line in there. On a miss, you count the number of ways occupied in the set by this application that's causing the miss. If the application is occupying less ways than you have given to it, as decided by the partitioning algorithm before, then you select the victim to replace from some other application. Right? If the application is occupying equal or greater ways than the ways that are allocated to it, then you select the victim from that particular application that's trying to bring the data in. Make sense? This is basically protecting, either trying to give more ways to the application if it's not using all the ways it's occupying, it's supposed to occupy, or if it's already occupying the number of ways, basically it's selecting the victim from the application itself. So this is one way of enforcing way partitioning. Not the only way, but it's doing it, if you look at it, it's doing it on a per set granularity because the distribution of the accesses may not be the same across all of the sets. One way to do this could be you give this way to this application, these 3 other ways to this other application, but that doesn't work because the distributions may not be the same across all the sets for different applications. So you really do this on a per set basis. But there may be other ways of doing it also. OK, so performance metrics. Let's look at how does this perform. I'll take this opportunity to talk about performance metrics a little bit so that you think about performance in multi-core, because it's not an easy thing to measure also. So one thing could be this, right? The one metric that people have used in the past in multi-threaded processors is this. You basically sum up the IPCs, instructions per cycle, for different applications. I have 5 IPC for this application, 0.1 IPC instructions per cycle for this application, 5.1 is my aggregate IPC. It's not the best metric. If you're optimizing for purely instructions, it may be OK, but usually you're not optimizing for that. So it's always good to think about, whenever you design a metric, it's always good to be adversarial about the metric. Can I game this metric? Now, the way of gaming this metric is, if an application has high IPC already, it's probably easy to give more IPC to that. As a result, prioritize that high IPC application. Right? Prioritize all the high IPC applications. That way, you can actually get higher instruction level throughput. This should really be called instruction level throughput. But the applications that have low IPC may starve. Right? So this metric actually can be unfair, and people have actually shown that. So people developed other metrics that take into account the baseline performance of an application in a normalized way. So this is one metric. It's called weighted speed up. Basically, it's the sum of these values for each application. IPC of the application when it's running together with others, divided by IPC of the application when it's running alone. That's basically the slowdown of the application. It's the sum of slowdowns, essentially. or sum of speedups, whichever way you like to think about it. So this is called the weighted speedup, and people have shown that this correlates with system throughput under some conditions. We're not going to go into that. You can read this nice paper that was published in 2008 that talks about it. But this is a bit more fair because it's really looking at the baseline performance of the application. If the baseline performance of the application is 0.2 IPC, and if you're improving it to become 0.4, now this is actually doubling the performance of that application. Whereas here, 0.2 to 0.4 is relatively only 0.2, right? Okay, so this basically is more fair. And there's also another, which is the harmonic mean of speedups, harmonic mean of these values over here. That balances fairness and performance, and it actually correlates with the reverse or inverse of the average normalized turnaround time of jobs. But you can again read that paper to understand that more. We're going to look at some of these metrics relatively quickly for utility-based cache partitioning. You can read the paper for more detail. But basically, these are two core workloads. We're assuming a very simple multi-core, 2 cores. This works beautifully if you have 2 cores. We'll see the scalability issues. If you have LRU, look at the geometric mean over there. Okay. If you have LRU, this is the weighted speedup that you get, the first metric. And if you actually have private caches, do half and half partitioning, static partitioning, which is essentially private caches, you get very similar to LRU. Sometimes better, sometimes worse. Okay? If you have utility-based cache partitioning, the performance is much higher, as you can see. And clearly, there are some cases where it's much, much, much higher, right? So you get the performance with this. What about, I guess, fairness? So let's look at the IPCs of the individual benchmarks. The red benchmark and the blue benchmark in each of these cases. These are 2 core combinations. And the first bar is LRU. The second bar is utility-based cache partitioning. And you see that the performance improves compared to LRU, of course. But there are some cases where the performance of an application, the blue application doesn't degrade, but the red application improves a lot, which is good, which shows that you're really inefficiently utilizing your cache with LRU. There are some other cases where the performance of the blue application degrades, so it's a trade-off. The performance of the red application increases significantly, much more significant. So you're gaining performance because one application benefits more from the cache, even though you're reducing the performance of the other one a little bit. And there should be some cases where both applications gain also, but I'm not sure if it's seen over here. That would be interesting, right? Now, those things happen if there are complex interactions with prefetching, for example. In this case, prefetching is not there. Okay. Okay, so any problems with this so far? Well, I've given you 2 core results, right? How does it scale to 1,000 cores? Well, maybe you don't want to share a 16 megabyte cache across 1,000 cores. That's fair. But how does it scale to 16 cores? And if you have 16 ways? So way-based partitioning is actually a problem because it's not scalable. But okay, even let's not go into the way-based partitioning. Let's look at the partitioning algorithm. The time complexity of partitioning is low for 2 cores, actually, because the number of possible partitions is actually equal almost to the number of ways. But possible partitions increase exponentially with cores. For example, for a 32-way cache, if you have 8 cores, the possible number of partitions is 15.4 million, which is not good. You can do the calculations. It's not that hard. You guys have taken probability, right? Which is clearly not possible with the partitioning algorithm we discussed, right? So the problem is NP-hard. Actually, you need a scalable partitioning algorithm. So people use heuristics with any kind of NP-hard problems. One heuristic is actually developed much earlier in the past. This is 1992. Harold Stone, also the person who actually did the logic and memory computer in 1970, if you remember our lecture in processing in memory. He basically was also concerned with optimal partitioning of cache memory at that time, more at the system level. And he wanted to minimize the overall number of misses in a cache. So he developed a greedy algorithm that basically allocates one block to the app that has the maximum utility for that one block. And it keeps repeating until all blocks in the cache are allocated. So it's a block-level partitioning algorithm, actually. And it provides optimal partitioning when utility curves are actually convex. But it suffers with utility curves that I'll show you over here, for example. So if the utility curve actually is flat like this, clearly you don't, if you look at the next block that you allocate, let's assume that block is equivalent to way over here. Doesn't matter, it depends on your granularity only. If you just look at the next block, well, you see that there's no utility that this application gains, right? But if you looked a little bit ahead, this application actually gains a lot if you had given it 22 blocks, right? 22 ways. So if you're myopic in what you look, then you will miss the longer distance. So that's the problem with this algorithm. You should not be myopic. You should look at the bigger picture of this mist curve over here. So basically, if you just look at the first block, you keep allocating to this application, whereas this application will suffer. So it has a look ahead of only one block. So let's take a look at the problem with that. This is application A and application B. This greedy algorithm considers the benefit only from the immediate next block, one more block. Hence, it fails to exploit large gains from looking ahead. Let's take a look at that. So in each iteration of this algorithm, you look at the utility for one block. For application A, the utility of the next block is 10 misses. You get rid of 10 misses if you give it one more block. Utility for this application B is just 0 misses. You don't gain any utility. In the next iteration, same thing. Utility of A is 1. If you give it one more block, you reduce the miscount by 10. Whereas B, you don't reduce the miscount. As a result, you keep giving cache blocks to A only. And this poor guy suffers. Right. So there's a problem without the look ahead. All blocks are assigned to A, even if B has the same misreduction with the fewer blocks. So how do you solve this? You need a better algorithm. You need more look ahead in the algorithm. So instead of looking ahead only for one block, you look ahead and consider marginal utility for all possible allocations for that application. Now, this is less complex than all possible partitionings that you give, which is really exponential. But in each iteration, you look at all possible net allocations. Let's take a look at that. You select the application that has the maximum value for this marginal utility that with this look ahead and allocate it as many blocks required to get that maximum marginal utility. And you repeat until all blocks are assigned. Let's do it pictorially. The same example, but we're going to look ahead. In the first iteration, we're not going to look ahead only for one block. We're going to look ahead for all possible allocations. And you will figure out that the marginal utility of A is really, you get 10 misses reduced if you allocate it one more block. Right. For B, marginal utility is actually, you get 80 misses reduced if you allocate it 3 blocks. Right. So its marginal utility is actually much higher than A. As a result, you start with allocating to B. So B gets 3 blocks in the first allocation. In the next 5 iterations, B's marginal utility is 0 because it's bottomed out over here. Whereas A has marginal utility of 10 per one block in every iteration. As a result, it gets the remaining 5 blocks in the next 5 iterations. Right? And this turns out to be the optimal partitioning in this case. And the time complexity, if you're really interested in this, you should really do the calculation yourself and read the paper, which is much better than what we've seen earlier. It's scaled with the quadratically with the number of ways. Okay, that sounds reasonable, right? Basically, look ahead as opposed to being myopic. So how does this perform? Read the paper for more detail, but this is LRU again. These are different mixes. And I think these are 4-core mixes. Yeah, they are 4-core mixes, sharing a single 2 megabyte 32-way L2 cache. If you do the greedy algorithm that we discussed, the block-based algorithm by Harold Stone, you actually lose performance sometimes, but usually you're okay. If you do the look-ahead algorithm, you get almost the same performance as evaluating all possible partitions, like what we've discussed early on. But this is not scalable, clearly. Okay, let's look at advantages and disadvantages over LRU of this approach. I think we've talked enough about utility-based cache partitioning. Clearly, we improve system throughput compared to LRU. You better utilize the shared cache. Disadvantages, well, we have not talked about fairness and quality of service. Maybe this is a limitation. It's not designed for fairness and quality of service, right? So if you may actually have, even with the look-ahead algorithm, you may actually have 2 applications that benefit from the cache, but they benefit at different rates. The marginal utility of one application may always be higher than the marginal utility of another application. So you run into essentially starvation in the cache for the application. That's unfortunate, right? And there are a bunch of other limitations. Scalability is still a problem. Partitioning is limited to the number of ways. What if you have a number of ways that are less than the number of applications? Well, or what if you have a number of ways that are close to the number of applications? You have another problem, number of cores. So I'm using cores and applications interchangeably over here. If you add threads on top of this, it'll be much more, of course. Scalability is another problem. We've talked about distributed caches, right? This is nice, perhaps, if you have everything, the tag store, in one place. What if you have a distributed cache across the core? How do you figure out all this information? How do you aggregate it? So this is an open problem, actually. How do you design distributed caches, and how do you actually partition the distributed caches? Well, there's always this question also, but that's usually the problem with any of the mechanisms that we've discussed in the past also, right? We're usually relying on the past behavior as being a good predictor for future utility, right? But if this is not the case, then this won't work clearly. Well, let's look at some other ideas in this direction. Any questions on utility-based cache partitioning? Okay. I'll cover this idea, and then we'll take a break. So this is actually an early paper also in the area. The goal of this paper was similar to stall time fair memory scheduling, although this doesn't really try to estimate slowdowns. It's going to approximate slowdowns with something else that we will see. Basically, the idea is to try to equalize the slowdowns of multiple threads sharing the cache. And the idea is to dynamically estimate the slowdowns due to sharing and assign cache blocks to balance the slowdowns. That would be nice if you can do that. We're going to take a look at that if there's time in the end. And approximate the slowdown with change in miss rate. So the idea was first proposed in this paper, and I'm going to discuss that a little bit. Basically, let's assume that you do partitioning at intervals, and you have two cores, processor 1, processor 2, and you keep looking at miss rates. You give some partition in the first interval to the different applications. Let's assume you have equal partitions. In a 512 kilobyte cache, processor 1 gets 256 kilobytes, and the processor 2 gets the other 256 kilobytes. And let's assume, again, you know the miss rate that you would get if you were running alone. So these are a lot of assumptions in the paper, but I think the high-level concept is interesting. That's why I'm giving it to you. So processor 1's miss rate, if it's running alone on the 512 kilobyte cache, the entire cache, it's 20%. Processor 2, it's only 5%. When they're running together, the system, the cache controller, computes the miss rates, call that miss rate shared, and figures out that processor 1 is getting 20% miss rate, processor 2 is getting 15%. And it computes the slowdowns in terms of the miss rate. It's not really a slowdown, it's really miss rate increase, if you will. But it's called slowdown in the paper, so I'll keep it that way. So for processor 1, it's nothing. The miss rate doesn't increase. But for processor 2, the slowdown is 3x, right? So clearly there's some unfairness. So you change the partition. You allocate more cache space for processor 2 and less cache space to processor 1. And you run for a while. You figure out the miss rate shared. So hopefully it has reduced over here. It's 10% now, but this is still at 20%. And the slowdown is still high for this one. As a result, you repartition again. You get more cache space for the application that has been slowed down the most, and less cache space for the other application. And then you run again, and assume that this is what you get. The cache miss rate of this one increases, and this one doesn't reduce by that much. So maybe you decide to roll back. Maybe you decide to go back to the previous partition, right? That's one possible thing to do. So take all of this with a grain of salt. This is basically, hopefully gives you the complexity of the problem. I'm not advocating this is a really good solution to the problem. But basically, you need to partition, repartition. And there are a lot of things that play into this, right? How do you define unfairness? When do you decide going back to a previous partition? What is the partitioning granularity, right? How do you do all of this? It's not that easy, I think. So you may decide to go back to a target partition, and you keep basically changing partitions. It's different from utility-based cache partitioning, but it provides something that the utility-based cache partitioning doesn't provide, which is more fairness, with this definition of fairness, right? Yes? Yeah, you can certainly augment this with different hysteresis. You can decide, oh, I won't change the partition if there's not a significant change in the miss rates or unfairness rate. But all of these actually complicate the system also. So this, in a sense, this should be a little bit similar to the fairness via source throttling that we've discussed, right? It's applying a similar approach, but the approach is not throttling clearly. The approach is partitioning here of the space, but there are a lot of moving pieces. There are a lot of thresholds that you need to optimize in a system like this. Okay, so let's take a look at the advantages and disadvantages. So in this case, you can reduce starvation, right? Because you have a baseline miss rate that you're trying to target or trying to not deviate too much from. And you get better average throughput on average. I'm not going to show you the results over here. So this is actually better than LRU, for example, also free-for-all sharing. And this provides block granularity partitioning. So if you have this sort of approach, you don't need miscounters, right? Because you really, well, you don't need per-way miscounters because you're not really trying to get the utility of a block. You're really just measuring the miss rate. But you need to know the alone miss rate. That's one of the Achilles heels of this mechanism. How do you get the alone miss rate? And we're going to talk about that at the end. Alone miss rate estimation can be incorrect. This paper actually assumes that you have a profiling run that gives you that. But that's actually very dependent on your input set. Is it scalable to many cores? This is always a problem with any kind of cache partitioning mechanism, actually. How do you scale it to many cores? Now your thresholds become even more complex. Is it a good fairness metric? That's always a question, right? Is the miss rate slowdown a good fairness metric? Maybe not. Does it provide performance isolation in the cache? The answer is no. Because again, it's very heuristic based, right? It's not trying to estimate the real slowdown. Unless miss rate slowdown correlates with real slowdown, which it doesn't actually. Okay. Any questions? Okay, this is probably a good place to stop and take a break. How about we take a 7-minute break and be back at 24? Okay, you guys are right on time. All right, let's continue. So now we've seen two different approaches to hardware-based shared cache partitioning. We're going to look at a completely different approach, software-based. And hopefully one of the big takeaways you'll get from this course is being comfortable with everything across the stack. Whatever you can do in hardware, you can do in software, and vice versa. It's all about the trade-offs that you get and how you optimize. I like this because this is a fascinating way in which the hardware interacts with the software. I'm going to close this. There's some sound over here. Yeah. Okay, no one is coming. Okay. I guess I'll move over here. It's a different place, different perspective. Always good to have different perspectives. Okay, so let's assume we have no hardware support in this case. There's also a middle ground, right? Software, hardware, cooperative parts. We're not going to talk about that as much, but assume we have no hardware support. We have demand-based cache sharing, i.e. LRU replacement. How can we best utilize the cache? There are multiple ways of thinking about it. One is using thread scheduling and not cache partitioning. I'll very briefly mention this. Basically, the operating system, if it can figure out the workload's working set sizes, for example, or miss rates, it can select the workload that place nicely together in the cache. Put together two applications combined, which combined have a working set that's smaller than the cache size, or access patterns that are nice. Don't put an application that's streaming through the cache and destroying locality of another application that has very good access locality. It may be okay to put together two applications that are both streaming and not utilizing the cache well, right? So there are a lot of heuristics that need to go into this also to understand how this works as well. But then if you put together very cache-unfriendly applications together, you may be causing a problem in the main memory level, right? So you need to be very careful. You're not just optimizing the cache, right? So this requires static or dynamic profiling of application behavior, and there are several papers that are written on this. This is one of them, one of the earlier ones, actually. If you're interested, you can take a look at that. We're going to talk more about cache sharing aware page coloring, basically how to partition the cache at the operating system level. And the idea will be to monitor the miss rate dynamically over an interval and change the virtual to physical mappings to minimize the cache miss rate. Of course, you could minimize something else also, but if you do this, you could minimize the miss rates. Right? You can try out different partitions again. So in a sense, it's a bit similar to utility-based cache partitioning in the sense that you need to decide the partition size, but the way we do the partitioning will be very different. And these are the two papers that I would recommend. I'm going to talk more about and borrow some slides from this paper, actually, which is a nice paper. But there are earlier papers on this topic also. So there are two ways you could do this. You could do this statically. Whenever an application starts execution, you predetermine the number of cache blocks that it needs somehow, maybe from information that's collected from past executions, and allocate that number of cache blocks to that application at the beginning of its execution, which means that other applications you may need to change also, right? The number of blocks that are allocated to those other applications. So even though it's static, you statically decide the number of blocks you allocate to each application, but you still need to change the partitions. Basically, you divide the shared cache to multiple regions and partition cache regions through OS page address mapping. We're going to look at the address mapping. Dynamic is hopefully better. You adjust cache quota among processes dynamically using something called page recoloring. This also requires page recoloring potentially, but we're not going to talk about this as much over here. Basically, the key question is, when do you decide the number of blocks that is allocated to an application changes? Do you do it at the beginning of the application when it gets scheduled, or do you do it periodically? And this has impact on overhead, because if you do it at the beginning of an application, okay, maybe you pay the cost of reconfiguring your cache once at the beginning of the program, and assuming programs are really long-running, that cost may be negligible. But if you decide, you monitor the cache miss rate, and you decide the number of blocks you allocate to an application dynamically, then you'll need to do this changing of the cache quotas or cache partitions periodically, and that actually causes a lot of overhead. And we'll see the overhead. The overhead really comes from what's called page recoloring. You dynamically change the process cache uses through OS page address remapping. So what's this coloring? We've seen this before, actually, when we talked about channel partitioning, right? You can divide the physical memory into colors, and also bank partitioning a long time ago in several of these lectures. But we're going to do a more formal treatment right now, however formal it can get here. The physical memory is divided into colors, and colors actually map to different cache sets, just like I show over here. Different indices into the cache can be controlled by the operating system, and we'll see why. Basically, let's assume that they can be controlled. You have these 4 different colors in main memory pages, let's say, and each page maps to different sets, as you can see over here. To partition the cache, the operating system only needs to ensure that 2 threads are allocated pages of different colors. And if this process is allocated, if this thread is allocated red and blue pages, the operating system knows that those red and blue pages will be isolated from these green and gray pages, and it can partition the cache. So it provides performance isolation also here. So this is a different way of partitioning. It's really index-based partitioning right now, right? Before we saw way-based partitioning and block-based partitioning. This is the index-based partitioning. So why does this work? We have the virtual address, as you've seen before. You have a page offset, virtual page number. This gets translated under OS control to a physical page number and a page offset, right? And you can interpret that physical address in a shared last-level cache, which is physically addressed. It looks like this. You get the cache tag, set index, and the block offset. And it turns out some of the index bits come from the physical page number. And the operating system has control as to which physical page number it can allocate to a given process, right? It can say all page numbers that end with bit 0 over here goes to process 0. All page numbers that end with all ones over here go to process 1. Now you partitioned the memory as well as you partition the cache. So if you do a physically index cache, basically you have these page color bits determining your indices. So this is called the color, basically. How many bits you have determine how many colors you have over here. Okay, so basically physically indexed caches are divided into multiple colors. All cache lines in a physical page are cached in one of those regions, one of those colors. And OS can control that virtual page, the color of a virtual page through address mapping by selecting a page with a specific value in its color bits. So these are the color bits. Okay, so let's look at static cache partitioning using page coloring. You have physical pages. You group them into bins according to their color. The operating system can actually do this. It's just some number of bits, right? And basically, this is the pictorial view of where they map into the cache. And then whenever the operating system allocates pages to a process, it chooses particular colors. And some other process chooses some other colors. As a result, you partitioned your cache over here. Now, there's a cost. Main memory space is also partitioned, right? because main memory space is now colored as well. By partitioning your cache, you're really partitioning your main memory as well, right? So you need to be careful with this, because you don't want to optimize something small over here to have huge overhead somewhere else, right? Because partitioning your memory may lead to page faults for a process. So you got to be very careful in the sense that you don't increase the page faults over here. If you're increasing the page faults, maybe you don't partition your cache. Maybe you can tolerate the interference that you have in your cache, right? Because a page fault can cost milliseconds, right? Okay, so that's always the cost with OS-based page coloring mechanisms. You partition not only one part of your system, but also some other parts. Memory channel partitioning, again, remember when we talked about memory channel partitioning, I said the same thing. If you do it very strictly, you may increase the number of page faults. That was the same thing. And actually, memory channel partitioning has an effect on the cache also, which we didn't discuss at that time. Now you're seeing that effect over here, but more explicitly in the cache. Okay, so let's look at dynamically doing this. Let's look at, let's say these are the allocated colors to a particular process. And how do you do this? Basically, you organize the pages of a process into linked lists by their colors. This is one way of doing it. And the memory allocation guarantees that pages are evenly distributed into all the lists to avoid hot points. And this is actually a problem when you do page coloring, because you have a lot of pages of red, green, and yellow in this case, and you want to balance them perhaps, right? There are a lot of other considerations here that we're not going into, but assume that you've nicely balanced this, right? It's beautiful. You have equal number of pages in each color. Now your cache, you're monitoring your cache, and you decide to allocate one more color to this application. What do you do? Well, this is a lot of data movement now, right? Well, you can pick and say, oh, these pages, somehow I'm going to reallocate in this color. Now, what does that mean? You really need to move those pages. Copy memory contents from this physical page to this physical page of some other color, because these are really different locations, and free the old page. And you do that, and you achieve some other balance. Right? So there's a lot of cost associated with this, right? We moved 4 pages over here. That's 4 times 4 kilobytes of data movement. Right? Actually, you read 4 kilobytes, and you write 4 kilobytes. And then you need to adjust the operating system page tables also, right? So dynamic cache partitioning is actually a lot of overhead if you do it at the operating system level, as you can see, at least without any hardware support. You can do this in today's systems. You could actually test it. You could go to your Linux kernel, change the memory manager. You can do all of this, and some of it is actually implemented in the memory manager. But the downside is a lot of overhead. Whereas with the hardware-based partitioning mechanisms, you could allocate a way. Remember the partitioning support, the third part. You just look at whether you've allocated the number of ways, whether you use the number of ways that are allocated to this application, and then depending on that, you make a replacement decision. Okay, so that's the cost of these mechanisms. So you still need to decide how much to allocate, and this is actually not trivial also, even at the operating system level. This is the algorithm that this paper that I mentioned provides. In a dual-core system, how do you do dynamic partitioning? Initially, you can partition the cache as 8 colors to this and 8 colors to that. And you run that current partition for 1 epoch time interval, and you try out different partitions, and then you choose the next partitioning depending on what you see. If an application benefits from another color, you give it that color. So, of course, this is not an optimal approach, and the optimal approach, again, is NP hard. So people use heuristics for this. I'm not advocating that this is the best approach. In fact, this is prone to a lot of issues. But this paper actually shows that it works on a real system. This is the system of its time, again, 10 years ago or so. And what they've shown is, you don't need to worry about all. Basically, they categorize the applications based on different types. And they show that both static and dynamic partitioning works, but maybe they work for different workloads. So for some cases, for example, static partitioning is better because you don't have the huge overheads of dynamic partitioning. There's a lot of repartitioning that needs to happen, and maybe you don't gain a lot of benefit from it. But there are some other cases where dynamic partitioning outperforms static partitioning because you really need dynamic partitioning over there. The static things are changing, and things are stable and changing, meaning they change, and then they remain stable for a while, and then they change, and then they remain stable for a while. But of course, there are some cases where you lose performance also. So for example, over here, 1.0 is baseline performance, and you're losing performance over here, regardless of whether or not you do static, or dynamic partitioning. But overall, these are the average numbers, as you can see over here. There are some workload combinations, for example, where you get 30% performance improvement with static partitioning. And on average, you improve performance. But you do need to do this carefully. And again, how does it scale is a question, right? Does it sound interesting? Maybe? Is it clear? Is it a good approach? Well, if you don't have any hardware support, this is how you partition your cache, right? And again, if you're really interested, you can go into the Linux kernel and do this thing yourself. Do the partitioning and see its effects. Okay, so let's look at the broader software versus hardware within the context of this page coloring. Now, clearly, there's a huge advantage. There's no need to change hardware. You could implement this today, right? Maybe easier to upgrade and change algorithm because it's not burned into hardware now. That's usually the advantage of software in general, right? But there are a bunch of disadvantages also. Now you have a very large granularity of partitioning, right? You're page-based versus way or block-based. And you need to move those huge pages. And you may actually have limited colors, depending on the cache configuration you have, how many bits of the physical address overlap with the page, with the cache set index. Now you may have very limited colors, right? You may have reduced performance per application because you have limited physical memory space. Remember, you're partitioning the memory as well. So you need to be really careful. Maybe there's no way to achieve this partitioning because you may have limited memory space. And you have reduced flexibility because of the limited page colors. And also the large granularity affects the reduced flexibility. As I said, changing partition size has high overhead because it requires a whole page mapping change, a lot of data movement. So that overhead needs to be amortized for this to be beneficial. And adaptivity is slow. This is usually a problem with software-based approaches, right? Hardware can adapt every cycle, possibly, right? It's a lot less overhead to keep track of things in hardware. You need hardware overhead, of course. But you can adapt very quickly. Whereas software, you need to get information first. You need to basically move into the software, the operating system, so that it can make the decisions. And it needs to adjust the page tables, for example, in this case, to change the decisions. So adaptation is relatively slow. And also, not enough information may be exposed to the software, right? In hardware, you can add these counters, for example, utility counters. How do you do that in software? Actually, people have proposed utility-based partitioning mechanisms at the software level. It turns out it's harder to do. For memory, you have more information. For caches, you have less information because they don't get communicated as often. You can use performance counters to get that information, but performance counters are also limited. Okay. So a combination of software, hardware, cooperative partitioning may be a good idea, but we don't have time to really discuss it at the moment. Any questions? Anybody excited about implementing this in the Linux kernel now? That may not be a bad project, huh? Yeah, that's a good OS project, I think, actually, operating systems project. Okay, let's look at what I call private/shared caching. Now we're going to blur the distance between private and shared caches. As I said earlier, goal over here is to achieve the benefit of private caches, low latency, performance isolation, while sharing cache capacity across cores. And we're going to look at one idea. It's called adaptive spill-receive caching. And the idea is to start from this other end of the spectrum, not start from a shared cache, but start from a private cache. Start with a private cache design, which by definition provides performance isolation, but dynamically steal space from other cores that do not need all of their private caches. This is actually in the distributed. Now we're actually looking into more distributed systems. In the distributed systems, there's this idea of cooperative caching. Essentially, that's what it is. In a distributed system, you have caches across different places. They're private, but you can cooperate. You can spill some of your data if you need more space. You can use somebody else's cache. For example, if I'm doing some very heavy computation on my phone, I can use your phone, right? Your phone's memory space, I don't know, or computation utility. It's a very similar idea. So basically, some caches can spill their data to other cores' caches dynamically. So private caches are good because they avoid the need for the shared interconnect that we've discussed. Caches can be directly optimized close to the core. So you get fast latency, you get nice tile design, and performance isolation. You get some of these with distributed caches also, but they have their own problems. The problem here is when one core needs more cache and other core has spare cache space, you cannot share capacity. So one idea that was actually proposed about 10 years ago again also is cooperative caching, what I discussed earlier for chip multiprocessors. You spill an evicted cache line from this cache to a neighbor cache. And this work basically proposed whenever you evict a cache line, you spill it. And whenever this evicts a cache line, it spills it, ... That may not be a great solution because you don't necessarily need to spill all the time. So this caused a lot of traffic, actually, because of spilling. And the performance depends on the parameter. They had a spill probability. With some probability, you spill it to a neighboring cache. With some probability, you drop it. And all caches spill as well as receive. This is a limited improvement. So this paper that I'm going to talk about tries to do that in a robust manner with less overhead. And I'll give you the idea relatively quickly. You can read the paper in more detail. But basically, each cache can be a spiller or a receiver, but not both. That actually limits a lot of the traffic as well as interference. Lines from a spiller cache are spilled to one of the receivers. So as you can see over here, each of them are somehow magically marked as spillers or receivers. We will see how that magic happens. And evicted cache lines from the receiver cache are discarded. Makes sense, right? So basically, if you're a receiver cache, if you're not spilling, you evict it, and then it gets evicted. Whereas a spiller can spill. And with some probability, it spills to this cache. With some other probability, it spills to that cache. How do you adjust those probabilities? Now, it may depend on what's the distance between those caches also, right? How long it takes to access. So now you really have a distributed system problem at hand. OK. So one question is, what is the best n-bit binary string over here that decides who's a spiller and who's a receiver? If you think about it, this is really a binary string where each cache is allocated 1 bit, where the bit indicates whether the cache is a spiller or a receiver. So this work basically uses set dueling or set sampling, let's say. You divide the cache into 3 spiller sets, receiver sets, and follower sets. And follower sets are the winner of the spiller and receiver. So now if you're looking at this carefully, this is a little bit different from set sampling because spiller sets and receiver sets are different. Right? If you remember the MLP-aware cache replacement, we had one policy, and we had 2 policies that we were evaluating, and we were sampling the same cache sets, and they were both implementing the same policy. So we were actually making decisions based on the 2 different policies applied to the same cache sets. Here we're trying to look at 2 different sets of cache sets. Some of them are designed to be spillers, some of them are designed to be receivers, and the rest are followers. This is called dueling because it's really different sets of caches. You're really not. Alternative could be, well, in this case, there's no alternative, right? They cannot be both spillers and receivers because you will really have a problem over there. OK. Well, actually, there is, because we're going to use auxiliary tag directories over here. You can have multiple auxiliary tag directories dedicated over here. One is emulating spilling, and the other is emulating receiving, but you're doing it for the same sets. In this case, it reduces complexity by choosing different sets, but it adds more randomness to the process. OK, so you have one selection counter that decides which one to use, basically. If you have more misses to the spiller sets, you reduce the counter. If you have more misses to the receiver sets, you increment the counter. And then you decide which way it goes. Should this cache be a receiver, or should this cache be a spiller? And it's very similar to MLP-based cache partitioning, right? Not cache partitioning, MLP-aware cache replacement. OK. So with a single counter, you can decide. If this cache benefits from spilling, the follower sets will spill. If this cache benefits from receiving, the follower sets will receive. Now, you can do this for all the caches in the system. You just need to allocate different sets to be the spillers and receivers, because they're going to spill to the same locations, assuming the caches are designed the same way. So each cache have different spillers and receivers selected randomly. And each cache decides on its own whether it should be a spiller or a receiver. Make sense? OK, cool. I'm not going to go into the results with a lot of detail, but in multi-core, you need to be careful in how you actually evaluate. So it's good to construct different types of workloads, like some of them are here in this case, benchmarks that actually benefit from more cache. They're called takers. The benchmarks that actually have extra cache, they're called givers. Or maybe the other way around. Anyway, you can read the paper for more detail. But there are a bunch of categories for workloads, and this is the configuration. So in this case, configuration clearly matters, right? Your local hits are much lower latency than remote hits. When you spill, when you need to access data from some other core's cache, it takes longer. So there's another trade-off that we didn't discuss earlier, right? But this is more realistic, actually. So if you do this, design this algorithm and implement it, this is what you get. So this is LRU. This is some baseline without no spilling. And this is dynamic spill and receive. So you actually improve performance significantly. And this is cooperative cache partitioning, where you both receive and spill. So that's not a good idea. Having a cache as both receiver and spiller is not a good idea. And intuitively, it makes sense to think about caches as spillers and receivers, because if you think about this cache, for example, maybe this processor is using only a fraction of it. Maybe this processor needs much more than the cache it has privately, right? Okay. And this dynamic spilling and receiving, taking into account the number of misses, helps. Because, for example, if you're streaming through your cache, you're getting a lot of cache misses. You're evicting a lot of stuff. But the fact that you're monitoring the number of misses you get if you actually spill or receive ensures that you're not spilling a cache, an application that's not going to benefit from extra cache. Right? Because you're really looking at the number of misses you get if you actually spill. If you're not benefiting from spilling, then you're not going to spill. A streaming application that's not getting benefit from its cache will likely be marked as a receiver in this case. So even though it is populating its cache a lot, it's not benefiting. So somebody else will put cache blocks over here. Now that may or may not be a good idea, because now you may be destroying the performance of that application, right? That's why you need something else on top of this actually to manage the cache better. So this just deals with where you put the data. But even then, you actually get a good performance. So the only place is here actually where you don't gain performance because all of the benchmarks are givers. So you need some takers over here as well. Okay. Any questions? I went through this relatively quickly. There's a lot of implementation detail, of course, in any of these ideas, but the key is for you to know the high-level bits, right? Distributed caching, spilling, and receiving, these are all high-level concepts applicable to anywhere. It's actually applicable to computation also, but we're not going to talk about that. So, for example, the example that I gave you over there, if I have a really low-power phone, but if I need more computation, maybe I offload some of my computation to your phone, right? There are a lot of other issues related to that, but it's similar in that, at that level. Okay, so as I said, there are a lot of other issues in caching. Distributed caching is one example. So this is an example of a distributed cache. Basically, you have this is actually a tiled multi-core design. This is processor 6 over here. You have a core, you have iCache, Dcache, you have an L2 slice. Now, this could be private. This could be shared. There are a lot of design decisions over here, and you have an interconnect with routers connecting them. Now, if you actually are accessing some cache block over here, and if you keep frequently accessing it, you're traversing a lot of your core, right? So there are a lot of issues that are caused by distributing the cache. But this is a more scalable approach to designing a multi-core system. Now you're really tiling different cores and different components and stamping those tiles, if you will, and hopefully getting better performance. But now you need to manage the cache even more intelligently than what we've discussed. Because now there's another parameter, which is the distance, and also the contention, and how long it takes to access a particular cache block. And there's another issue that we have not discussed as much, caching for parallel applications, but that's true for non-so-parallel applications also. Like, where do you place the data in the caches determines your performance. One of the goals is to place the data on chip close to where they're used, but that doesn't always work. What if this core is accessing this data a lot, but this core is also accessing this data a lot? Now, where do you place the data? And this is a very complex optimization problem because it's not only about the data, it's also about the computation, right? Maybe you place your computation wrong. Maybe the cores that are accessing the data together in close time proximity, they should be put together in physical proximity also, right? Maybe those two threads should be placed in the cores that are adjacent to each other, right? Yeah. I'm not going to go into a lot of techniques or details. We briefly talked about it when we talked about the application to core mapping, but there's a lot more to be done. Let's talk about some other issues before we move to some other techniques. One issue is handling shared data in private caches. We talked about this briefly. Shared data unlocks ping-pong between processors if caches are private. Shared caches don't have this problem. And this ping-ponging is actually not good for scalability of a parallel application. Actually, if you parallelize your application, if you see it's reducing in performance, there are many, many reasons, of course, but one of the reasons could be this ping-ponging of shared data unlocks. This increases the latency to fetch shared data unlocks, and it reduces also cache efficiency because it causes many invalid blocks in your cache. And there's also another problem, scalability. How do you maintain coherence across a large number of private caches? It's actually costly. If you want to have 1,000 core processors, how do you maintain coherence across them? 10,000 threads. In a GPU, for example, how do you implement coherence? Do you want to implement coherence? These are actually research areas that people are looking into. So how do you do better? This is something that we will discuss later, actually. Maybe tomorrow, we'll see. Depends on how long, what we finish today. You can store the shared data unlocks in one special core's cache, and then you can divert computation on those to that core or that cache. Or basically send the critical sections that access shared data unlocks to a particular core that may be specialized for processing shared data unlocks. That way, the shared data unlocks stay in one place, and you may actually have a specialized core for processing critical sections. And we will talk about that later on. It turns out this actually improves your cache efficiency. This improves your performance because now that core can be bigger, can execute fast in those critical sections. Okay, let me go into some other topic. Any questions, by the way? You guys are quite silent. That may be good or bad. Is this good silent or bad silent? Good silent is you understand everything. These are good concepts. Who agrees with that? Just two people? Is it too fast, or am I going too fast, do you think? No? Okay. You don't necessarily agree with the first one, but not disagree with the first one. There are a lot of options, of course, yeah. Okay, please stop me if you have questions. Again, I don't expect you to understand the nitty-gritty implementation details. That's not the goal of this lecture, at least. Some lectures, maybe we do go into detail more. I do expect you to understand the high-level concepts, because the high-level concepts are really applicable in many, many places. And in the end, you will need to, when you implement it, that's what the labs are for. When you implement things, you will see the nitty-gritty details. And probably you don't want to see those nitty-gritty details all the time. Okay, so non-uniform cache access, this is actually an interesting idea. It's a little bit different from the distributed cache that we've discussed earlier. But it has similarities. Basically, the problem is large caches take a long time to access because of wire delay. Right? In DRAM, for example, we had this long bit lines. The same issue exists in SRAM also. You have this long bit lines. You could actually have blocks that are close by that can be accessed faster, but the furthest away block determines your worst case access time because of this huge capacitance on the long bit line, right? If you remember the tiered latency DRAM idea, we tried to segment that bit line such that some part of your cache was faster, some part of your DRAM was faster, some other part was slower, right? The part that's closer to the sense amplifiers that is segmented out when you isolate that part is much faster, right? It's a very similar idea. Make the caches non-uniform access. Tiered latency DRAM makes the DRAM chip non-uniform access. The idea is to have variable access latency in a single cache. So how do you do it? Tiered latency DRAM does it in a specific way by segmenting the bit lines. You could do it in the same way, actually, in a SRAM cache. Segmenting the bit lines is a very general idea that's applicable to any type of memory where you have bit lines. In this case, another way of doing it could be partition the cache into different pieces and interconnect them somehow. Each piece has different latency. Then there are many questions, right? Now, you could think of this as a distributed cache also, right? This piece that's close to the core is fast. This piece that's far away from the core is really slow. Now, there are many questions. Which piece does an address map to? You could do this decision statically based on the bits in the address. You take some of the bits and you hash them. You decide which cache it maps to. That block is always in that cache. Now, the problem is you cannot move the block to some other part of the cache. Dynamic, any address can map to any piece. Now you have an indexing problem, right? You need to have a tag store that's more complicated, and you need to locate the data. So how do you locate an address? What is the replacement and placement policy? When do you move? Let's assume that this core is accessing a block that's far away all the time. You figure that out. You need to figure that out somehow. And then you need to move the data or move the computation over there. So there's a lot of design space that opens up once you think about caches being non-uniform access in terms of both scheduling, mapping, replacement, placement, ... And this is one of the earlier papers that proposed this non-uniform cache idea. And the goal here was really to reduce the latency of access to a cache. It was really not to distribute the cache. The distributed caches came on top of that in a different way. Okay, so let's talk about some other thing. One of the other things in a multi-core system to think about is cache efficiency, and we're going to transition into that soon. Caches actually have another benefit in multi-core, which is they act as a filter that reduces the memory bandwidth requirements. And this is always true, right? Whenever you prevent an access to memory, you reduce the memory bandwidth requirements. You also reduce the latency of that access. But in multi-core, this is actually very important, as we've studied earlier. Bandwidth is at a premium. On a cache hit, you need no access to memory. And this is in addition to the latency reduction benefit. And this is actually one of the major reasons why GPUs have caches today. They're not there, because GPUs can tolerate latency very well, as you've seen the lectures, right? They have a lot of multi-threading. But they use caches to mainly reduce the memory bandwidth requirements. They exploit the locality. It's actually a really good interview question. If you go to NVIDIA, for example, or whoever manufactures a GPU, if they ask you a question saying, like, why do we use caches in GPUs? Your answer should not be latency reduction. Now, there are benefits to latency reduction also, but it's really there to reduce the bandwidth requirements because they can tolerate latency. Actually, the many applications they use are able to tolerate latency also because of the parallelism. But they cannot provide more bandwidth. They're really bottlenecked by the memory bandwidth. So they put caches to filter out unnecessary bandwidth consumption. And this becomes more important with multi-core. GPU is, again, a multi-core. Memory bandwidth is more valuable, and pin count is not increasing as fast as the number of transistors. As we've discussed earlier, pin count is increasing 10% versus 2x every 2 years. That's the 2x every 2 years for a number of transistors. 10% is every year, actually. We should fix that slide, huh? So online error correction. That's good. Now I've freed up you to think so you can actually use multi-threading to ask me a question. Okay, I didn't give you enough time to execute that thread, maybe. Okay, you can still ask questions, though. Okay, so more cores put more pressure on the memory bandwidth, clearly. So a key question that people have been obsessed with for a while is how to make the bandwidth filtering effect of caches better. And if you design caches at NVIDIA, ARM, people who design caches, you will actually need to deal with that problem, actually. So let's talk about efficient cache utilization, because that essentially ties into what I just said. Let me move over here maybe for a while. So we're going to talk about these papers. Well, I think you know the first one, so I'm not going to talk about the first one. But let's start with the second one over here. This paper actually has a lot of impact also on how caches are designed, and some of the ideas here are employed in existing systems. We're going to revisit cache placement or insertion. And we're going to ask the question again. Remember, I asked this question earlier also, but it's now more important now. Is inserting a fetched block into the cache always a good idea? We've seen this answer for writes. Maybe you don't allocate on a write. It doesn't allocate a block on a write miss. So that's one way of not inserting. But writes are not the only things. What about reads? If you allocate a cache block on a read miss, you evict another potential useful cache block from this application or another application. Right? Of course, there is also a benefit, right? Incoming block potentially is more useful. So how do you actually make this decision? Ideally, we would like to place those blocks whose caching would be most useful in the future, right? For some definition of most useful. And we certainly do not want to cache never-to-be-used blocks. So maybe there's some simple things that you can do. So never-to-be-used blocks, you don't want to cache, right? So there are a bunch of ideas over here. Hardware can predict blocks that are not going to be used. And there have been papers that have been written there's actually a nice paper that talks about this like 22 years ago now. And this is also called dead block prediction. You could do this prediction at the software level. Maybe if this programmer or the compiler knows that some instructions touch data that's not going to be reused, they can tell that. And you could do that in an Intel architecture, for example, with prefetch NTA instructions, non-temporal instructions, non-temporal loads. Of course, the architecture may not always do what you really want. You may not have enough control. So I don't have the latest manual, but I think prefetch NTA, the non-temporal loads in Intel x86, it's microarchitecture dependent, its definition. So if you mark a load as non-temporal, I think in most implementations, it doesn't bring the data into the L1 cache, but it still brings the data into the L2 cache. So maybe that's limited, right? That's not what you necessarily want. So you don't have perfect control over the cache hierarchy today as a software programmer. Now, if you have complete control, maybe you do better, but then you may go crazy also, right? You may optimize your program for this processor, and the next processor has a completely different cache hierarchy. What do you do? OK, so clearly, you can do this in software and hardware also. But we're not going to go into a lot of detail over here. So streaming versus non-streaming accesses is actually a key definition, distinction between different types of accesses. If a program is streaming through data, reuse likely occurs only for a limited period of time. And then you're really streaming on, think about this like you're watching a video, right? You're really streaming through the entire video, and you're operating on very little piece. You don't have a whole lot of temporal locality, perhaps, right? You have a lot of spatial locality. So if somehow you mark such instructions by the software, the hardware can store them temporarily in a smaller buffer to capture that small temporal locality instead of the cache, right? So this idea becomes similar to prefetching. In fact, there have been studies that show that if all you're doing is streaming through memory, always sequential accesses, you always prefetch into a small buffer, and you basically keep evicting from that buffer in a regular fashion. Right? You don't have a cache, as we discussed. You don't do Lru policies, but you stream data. In fact, you can automatically do it, right? If you see the pattern, I'm always accessing address A+1, A+2, A+3, A+4. You keep streaming data into a buffer. And if that buffer is large enough, you capture the temporal locality, and the incoming data automatically evicts the data from which you've already captured the temporal locality from, hopefully. So that's a key distinction, actually. OK, so let's take a look at reuse at the L2 cache level. This is data from the paper that I am going to describe, the Dynamic Insertion Policy paper. But one of the things that this paper shows, and previous papers also showed, is that you have a bunch of blocks that get placed into the cache, and they're not used between insertion and eviction. Basically, they're dead on arrival, as in this paper's terminology. And if you look at some applications, this application, ART, it's streaming through memory. 90% of the lines, cache blocks that are inserted are not used before they're evicted. And this guy is streaming very, very heavily through memory, right? 100%. Well, why? Why is this happening? On average, 60%, which is really high, actually. And I've actually personally done many of these studies in different places and found that this is really high, even in the L1 cache. But this is L2, actually. So basically, you get ineffective use of cache space. But one of the reasons why this is happening, at least in the L2 cache, why this is so high, is the temporal locality is captured at the L1 level. There's another cache on top of this. You're inserting there and inserting also into the L1. And L1 is inserting also into the L2. L1 is capturing the temporal locality. So you keep hitting in L1, maybe. Maybe the insertion to the L1 is not useless. But insertion to the L2 is useless because you already captured the temporal locality in L1. And you're not going to need the same cache line in L2. OK, so there's a number of solutions to this. Maybe you have not inclusive cache hierarchies. When you bring a block, you don't put it in all of the caches. You put it into L1, monitor what's happening to it, and then you decide whether you put it into L2 or not, right? That's an idea that has been proposed that some processors actually implement. This is called a non-inclusive cache hierarchy. You could make it really strict and make it exclusive cache hierarchy. Exclusive means a single block exists in only one of L1, L2, L3, let's say. Only one part of the hierarchy. Right? So that's one solution, which we're not going to talk about. Let's talk about some other solution. So like basically, you have one observation is that streaming data is never used. L2 caches don't help. Right? Never may be strong. If you have small temporal locality, maybe the temporal locality is captured by L1. Right? And the other reason is you have working set of an application greater than the cache size. Right? For example, in this case, this application, its working set is really greater than the cache size, right? You want, without giving it a lot of cache blocks, like a 2 megabyte cache, you're not going to reduce its miss rate a lot, right? There's a huge jump over here. Again, here, without giving MCF 3 megabytes, which you may not have, you're not going to get much benefit from caching. You'll reduce maybe a little bit, but not a whole lot, right? So one of the solutions could be, if the working set is greater than the cache size, retain some working set. Right? And that's actually not a bad idea if you're scanning through memory and if you have some reuse. So let's revisit the insertion policies that we've discussed. This is most recently used. LR, here things get a little bit odd in terms of terminology. But if you think about least recently used replacement, it requires you to insert in the most recently used position, right? When you're inserting a cache block, you insert that as a most recently used block. So basically, if you reference I, cache block I, it needs to be inserted over here, and everything else needs to be shifted. That's why it's a stack algorithm, right? You put it on top of the stack. It's an LRU stack, and you insert on top of the stack, and the last thing gets kicked out, the least recently used one. Now there's the opposite of this. Let's call this LRU insertion policy, which is a really bad name. But you basically insert at the LRU position. Instead of inserting at the most important position over here, you insert at the least important position, next to be evicted position. You evict H. You don't evict these important ones, perhaps. Basically, you don't promote the incoming block to MRU. And maybe you monitor what's going on, and if you get another hit over here, you move it up here. That could be one policy. And actually, existing processors implement a variant of it. I'm happy to discuss it separately, but I'm not going to talk about that right now. Usually, they insert not at the top position. They basically insert somewhere else, monitor it a little bit, and if they see some reuse, they move it up there. OK. So this paper is actually one of the earlier papers that discuss some of those ideas. That's why I'm covering it. So one of the issues with LIP, this LRU insertion policy, is it really doesn't age older lines. Existing processors actually do it, but that came later. So one of the ideas is infrequently insert lines into the MRU position. I like this because this is really simple, and it gives you ideas also. So let's assume that you have a random number generator. You generate a random number. If it's less than some really small probability, let's say 1 over 32, you insert the block, incoming block, at the highest possible position. And if it's less than that number, if it's greater than that number, you insert it at the lowest possible position, which is this one. So most of the time, you insert the block over here. Some of the time, very little of the time, you insert it over here, probabilistically. Now, why does this make sense? If you have reuse, hopefully, you'll hit on that block, and you're going to move it to the MRU position anyway. But if you don't have reuse, most of the blocks will be inserted over here, and they will get kicked out soon. Right? That's the idea. And if you have enough sets in your cache, inserting only into the LRU position may be OK, because maybe someone else will not evict this before it gets reused. Right? But that's the probabilistic part. Basically, this prevents the thrashing that happens, like we've discussed. If you're streaming through data, you're really evicting all of the cache blocks, the useful ones, useless ones, everything. That's called thrashing. We're going to define it better later on. But it retains that thrashing protection. So this policy, inserting at the lowest priority position, is good for thrashing because you basically, if you're streaming through memory, everything just uses the LRU position all the time, right? This other stuff, which may have some reuse, you don't touch them. They're protected. Right? Things only get here if you reuse them. Then they move over here. Or if they're inserted at the MRU position with very low probability. Right? So this gives you some adaptivity such that some blocks sometimes get inserted at the MRU position. Right? Does that make sense? This way, if your working set changes, you start inserting other stuff into the MRU position. So let's do some analysis. You'll need the paper for more detail, but we're going to assume a circular reference model, similar to what other people have assumed. And we're going to have a reference stream that has T blocks and repeats N times. I'll give you the model over here. I'll focus on this part first. Basically, cache has K blocks. K is less than T. So basically, we're streaming through an array. Block 1, block 2, block 3, block T. T is much greater than the number of blocks in the cache. And let's assume a fully associative cache to make life easier. And N is much greater than T. So you basically do this many, many times. Right? Now let's do the analysis of hit rate with LRU. Well, LRU gives you 0% hit rate. Because you're streaming through memory and you have more blocks than the cache can save, right? If you have the optimal policy, you will always keep the blocks that you're going to reference earliest into the future, which means that you're going to keep A1 through AK. You're going to keep the first K blocks in the cache, and you're not going to put anything into the cache. That's optimal, right? Optimally, you know the future. So you get this, basically, K minus 1 over T. You can do the analysis. And if you have the least recently used insertion policy, which is you insert always at the lowest priority block, basically you get that also, actually, for this. Because you insert, initially, although the blocks are invalid, you insert the first K blocks, and then everything else gets inserted in the LRU position. Right? You don't get all of the K, you get -1 because there's one thing that you keep evicting, right? So optimal is also the same, basically. There's one thing you keep evicting. Everything else, K minus 1, the first K minus 1 stays there. So that's good. You get K minus 1 over T. So with bimodal insertion policy, you get very close to K minus 1 over T because with a small probability of epsilon, you insert at the most recently used position with very small probability. You insert at the least recently used position with very high probability. As a result, you're very similar to this. Right, least recently used position insertion policy. So that's the analysis with this access pattern. Now let's say you have this access pattern, you operate on this array many, many times, N times, and then you move on to a different array. Blocks B1, B2, B3, B4. Now you're not going to reuse this anymore. You're done with this phase of the program. You move on to this. Now once you move on to this, LRU doesn't provide you anything. What optimal will do is, optimally, because you have this cyclic reference pattern, it knows that blocks 1 through K are the ones that are going to be reused earliest into the future. So it's going to cache those K, but then one block is used for eviction. As a result, you get K minus 1 over T. But the problem with the least recently used insertion policy, if you keep inserting only here, is you won't adapt to the working set size changes. Right? So here it gave you similar to the optimal, that's fine. But now it's cached A1 through AK in the cache. Or to be more precise, A2 through AK, A1 through AK minus 1, actually, to be precise. But now, things are moved. It didn't get aware of that. As a result, it keeps inserting the blocks into the LRU position. Every other cache block contains A1 through AK minus 1, which are not going to be referenced anytime in the future, so you get a 0% hit rate over here. The bimodal probabilistic insertion, the more general idea over here is probabilistic management, probabilistic insertion, enables you to adapt to the working set size change. Basically, working set size changes, you slowly put stuff into the MRU position with a small number of epsilon, with a small probability. But if you keep iterating over here, you actually populate the cache with some elements over here randomly. It's not B1 through BK minus 1. It's really random over here, right? Here, it's A1 through AK minus 1 because it's, again, this also changes. But you get performance that's close to optimal this way. Make sense? So basically, the takeaway over here is twofold. Thrashing is a problem if you have this kind of pattern. LRU is terrible at thrashing. Even inserting at the least recently used position is not good at adapting to behavior. So probabilistic approaches actually give you better performance. And some of this is used in modern processors. Okay, and this is from the paper. If you really want to do the analysis, you should really read the paper because it's really probabilistic. Okay, so let's take a look at the performance of this a little bit. These are single-core workloads. We're not going to look at the multi-core performance, but multi-core, this performs well also, but you need to have partitioning mechanism also on top of this. This is % reduction in L2 cache miss rate. This is if you always insert into the least recently used position, the lowest priority. Even that improves performance significantly on some workloads, as you can see. RTOS, for example, streaming, you get 40% performance improvement by a very deterministic policy that inserts always at the lowest priority position. If you do it bimodally, probabilistically, MRU versus LRU, with low probability insertion into MRU, you get better performance, as you can see. But sometimes you get not so as good performance, but it's not that bad. But as you can see, there are some workloads that are actually very, very LRU friendly, it turns out. And you lose performance in those workloads. So how do you get the benefit of that? Again, set sampling or set dueling helps you. So you cannot get away with, unfortunately, you cannot get away with having more than one policy in a cache. You really need these heterogeneous policies in cache management. I think you need heterogeneous policies everywhere because they adapt to different kinds of behavior. It turns out you have LRU-friendly workloads or bimodal insertion policy-friendly workloads. Which one do you choose? You monitor both policies using set sampling. You choose the best performing policy for the cache and apply the best policy to the entire cache. Now, if you do that, you basically get rid of all of these performance losses that you get with bimodal insertion policy. That's called the dynamic insertion policy. You keep most of the benefit of the bimodal insertion policy, and sometimes you do better, as you can see. And you actually curb all of those performance losses, well, most of them at least, by being more adaptive to the workload behavior. As a result, you get, this on a single core workload, basically 20% performance improvement, which is not bad for a single core system. Okay, and you can see more comparisons in the paper. Basically, the paper looks at different types of combinations of policies. LRU plus random, for example, is not a bad policy also. Random replacement, but it turns out this is more robust dynamic insertion policy. And this is the optimal policy, and this is doubling the cache size for the cache size that's evaluated over here. So you can get close to doubling your cache size without changing your baseline policy, right? Which is always a good thing. Okay, so if you're interested, actually this might be one of the papers that I will add as one of the readings. You guys are excited about doing the readings? Okay, some of them. Maybe there are too many of them. You can put that in your feedback. Okay. I mean, all of this is optional, of course, but actually, this course is optional, by the way. It just occurred to me now. Yeah. You're putting this pain onto yourselves on your own. But hopefully it's not pain, it's because you like it. Okay, so maybe this is actually a good place to stop before we move on to the next few ideas. Let's take a 6-minute break. I really want to cover both of these ideas before we finish so that we can move on to some other topic. So I get a good 6-minute break. Okay, I think our 6 minutes are up. Sorry. Hopefully you'll have a lot of fun with these ideas. Oh well. It's better, but not that great. If we can stop it in the middle, that's better, probably. I don't know. Yeah. Okay, so I'm going to cover 2 different approaches to improve cache utilization. Clearly, the adaptive insertion policies improved cache utilization, and there's a flurry of work after that also. So multi-core actually invigorated the cache problems a lot. I'm going to talk about one idea that covers multiple different problems in caching. Of course, cache utilization is important because of large latency, increasing contention. And it turns out different blocks have different reuse behavior, and we've seen that with different applications, but this is true for different blocks also. For example, some blocks have high reuse, some blocks have low reuse, right? Ideally, we would like to distinguish between them and store only the high reuse blocks in the cache. And there are many ways of doing it. We've covered some ideas. We're going to look at a particular way. So there are two problems. One is cache pollution. This is defined as low reuse blocks evicting high reuse blocks. Basically, you're polluting the cache because you're not utilizing it well. So LRU policy, for example, inserts everything into the MRU, so it's causing cache pollution. So the idea is to predict the reuse behavior of the missed blocks and insert low reuse blocks at the LRU position and high reuse blocks at the MRU position. So if you can predict that behavior, that's good. Right? We're going to look at one way of approximating that. And as a result, you would get this. So basically, insert high reuse block, low reuse blocks only into the LRU position and high reuse blocks everywhere else. Okay, the second problem is what you've seen, cache thrashing. And cache thrashing is especially worse if you have high reuse blocks evicting each other. So low reuse blocks, maybe you can get rid of them with bimodal insertion policy, for example. But if you have high reuse blocks evicting each other, some of it you can get rid of with bimodal insertion policy, but some of it may not. Basically, what's happening is you keep inserting into the cache high reuse blocks. And bimodal insertion policy gets rid of some of this, but not all of this, actually. Insert at the MRU position with a very low probability. Insert at the LRU position most of the time. Okay, we've already seen this. It gets rid of basically a good amount of the thrashing, but not necessarily all, right? A fraction of the working set stays in the cache over here. Okay, so you need to address both of these actually concurrently. Bimodal insertion policy doesn't address the first part, pollution, as much. And cache pollution, you need to distinguish between high reuse blocks from low reuse blocks. And cache thrashing, you need to control the number of blocks inserted with high priority into the cache. And bimodal insertion policy does a good job of that. Other papers have improved upon that later on, which you can read, or you can ask me for which pointers. We're going to tackle this problem a lot in this work. So the key question we have is, whenever you get a missed block, how do you determine whether it's going to be reused a lot or reused by little? You can keep track of the reuse behavior of every cache block in the system. That's impractical because it's a lot of storage overhead and lookup latency. Right? You really need to do it for the entire memory, not just caches. Or you can use a program counter or memory region information. These are approaches that were actually followed by a lot of prior works. So you can group the blocks based on the program counter, this load versus this load, and learn the group behavior, assuming one exists. And you can predict the reuse based on the program counter, right? Maybe this load is always bringing data that's not going to be reused into the cache. And that happens, actually. There are some cases where this holds true. If you can identify them, that's actually good. Non-temporal loads is an example for, where the programmer can hint which ones are high reuse, which ones are low reuse. But sometimes same group is not the same reuse behavior. In fact, there's a question over here. Should you look at the program counter? Should you look at the memory region, right? Is this a property of the data or is this a property of the code? And sometimes it's a property of both. So that's why this is a difficult problem. And there is no control over the number of high reuse blocks, even if you do this perfectly. So this doesn't have a thrashing protection. Okay, so per block reuse prediction uses the key idea over here is to use the recency of eviction to predict reuse. So you've already cached the block. You're evicting it. And if it's accessed soon after eviction, the key idea here is maybe you've done the wrong thing by evicting it, right? Because you're going to access it very soon. If it's not accessed for a really long time after the eviction, maybe it was okay to evict it, right? So that's the idea over here that we're going to try to exploit. Basically, look at the recency of eviction. When was the block evicted? When it was evicted. And if it's accessed close enough to the time that it was evicted, we're going to insert it at high priority into the cache. That's the idea of evicted-address filter. You have this cache. You have this evicted-address filter, which stores the addresses of recently evicted blocks. Whenever you evict a block address, you basically put it over there. How do you organize it? We'll look at that. Whenever you get a miss in the cache, you look up the block address. If it's in the evicted address filter, which means that it's recently evicted, you insert this block with high priority into the cache, predicting that it's a high reuse block. Basically, you've done the wrong decision previously. If it's not in the cache, you predict that it's low reuse block, and we're going to insert it actually with bimodal insertion policy, or you're going to insert at the LRU position over here. So one naive implement, how do you implement this? We're going to talk about implementation over here because this could be really costly, actually. Naive implementation is you can use full address tags and keep the address tags of all of the recently evicted addresses, and it still has a lot of overhead. But the realization is that this doesn't need to be perfectly accurate, so you could actually turn this into a Bloom filter. You get low storage overhead and energy. And you remember the Bloom filters. I actually foreshadowed this paper. Well, not this paper, but the paper that I'm talking about right now, evicted address filter paper, when we talked about Bloom filters in lecture 1, right? And this is a paper hopefully you guys have read, but it may be hard to read. It's old, but it's a good paper. Okay. So if you remember Bloom filter, this is another way of explaining it. This is from Vivek's conference presentation. This is my students' work. Basically, you have a bit vector, you have a set of hash functions, and you insert some elements. Let's say you insert x, it sets some bits. You insert y, it sets some other bits. You test whether x exists, you map to the same bits, and both bits are true. Then you basically Bloom filter returns that, okay, I have this. It's a hit. You test z, it maps to a 0 bit over here. You OR those bits that it maps to, and Bloom filter returns that I don't have it. And then you test w. It tells you have w, but it's because you have a false positive, right? So you know about this. You can get false positives in Bloom filters, but not false negatives. But you cannot remove individual address in a Bloom filter. That's one of the downsides of this data structure, right? If you want to remove an individual address, x over here, you cannot remove it because you may remove actually multiple. You may remove a bit that maps to some other address, right? You don't have enough bits to distinguish all of the addresses that you've inserted. Okay, so remove is not permitted, but clear is permitted, so you can clear the entire Bloom filter. So we're going to make use of that. So if you have an evicted address filter, we insert the evicted block address. We're going to test on a miss. We're going to test the miss block address and remove if present. We're not going to be able to do that remove, unfortunately. And when this FIFO or whatever data structure over here is full, you remove stuff at the end, and you keep inserting at the, assuming this is a FIFO. Now, when you turn this into a Bloom filter, you cannot do these. You can do the insert and test operations really fast, but you cannot do the remove operations. So we're going to get rid of that. We're going to clear when this thing is full. And there's a design space exploration that you can go through. Maybe you could use multiple Bloom filters, right? Such that things are graceful, but the paper has a lot more detail about that implementation. But what this buys you is a lot of reduction in storage overhead. You don't store all of these tags, and it's relatively small. So the final design is you have this cache, you have this Bloom filter and a counter. When you evict a block from this cache, you insert the address into the filter, you increment the counter. On a cache miss, you check if the address is in the filter, just like a Bloom filter, it's a Bloom filter. If the Bloom filter returns a hit, you insert the block at the MRU position because you've done the wrong decision by evicting it recently. Otherwise, you insert the block with the bimodal insertion policy to ensure that you have thrashing protection. So bimodal insertion policy is important because it's really a building block for many other policies that we have today in systems. Okay, and the counter reaches max, you clear the filter and the counter. And you can read the paper for more detail. So there are a bunch of advantages of having a structure like this. It's relatively simple to implement. It's not part of the cache if you think about it, right? We have not modified the cache at all. We're really operating at the outside of the cache. It's easy to design and verify, hopefully, and you can work with other replacement policies also. You just observe cache evictions and cache misses, and then use an insertion policy that's hopefully implemented in there. So the paper has a lot more detail, of course. This is a summary of the performance, and I'm not going to go over all of these cache mechanisms, but this tells you the different cache mechanisms that were developed in the past year. So this is the thread-aware version of dynamic insertion policy. What I described made thread-aware. Thread-aware version of dynamic re-reference interval policy, for example. And there's a bunch of other things. Some of these are program counter-based reuse prediction policies. And I'm not going to go into the detail of evicted address filter versus de-evicted address. Well, I will tell you. So even evicted address filter does not work well by itself. You need to, some workloads are really LRU friendly. So LRU is so strong, you need to figure out when LRU is good. If LRU is doing well, you pick LRU, basically. Otherwise, you pick the evicted address filter. So now we're complicating the policies, right? And it turns out it's good in some cases, right? So basically, the performance improves significantly compared to other policies. And you can read the details. So one of the reasons I will actually assign this paper as one of the readings, maybe the required reading. This is a really well-done paper, in my opinion, because it really covers a lot of work. Memory region-based reuse prediction. It's actually one of the earlier works that looked at reuse prediction as early as 20 years ago or longer. It's called runtime bypassing. You try to bypass the cache runtime. And program counter-based reuse prediction. And there are a bunch of other stuff. So I'm going to skip these relatively quickly. So if you look at this paper, this is actually a good way of presenting your results. Like if you want to do research in this area, it's always good to have curves like this. Now this is a large number of workloads, as you see, and this is the performance improvement over LRU. Now you can see a lot of these workloads. This kind of curve is actually used heavily in companies, for example. When you develop an idea and you pitch it at Intel, they will ask you, what does the S-curve look like? And they call this the S-curve. Because inevitably, a lot of the ideas look like S over here. This is an interesting S over here. Sometimes you have an S that looks like this. Sometimes you have an S that looks like this, which is a bad idea probably, because you have performance loss. So this is an S that looks like this. And this is evicted address filter. That's program counters-based reuse prediction. So you can see where you are compared on each workload point over here. So there are cases. So this actually matters when you're designing a general purpose processor or even a special purpose processor. You want to get rid of these cases as much as possible. You lose performance, but there are people who care about these cases. So how do you curb them? Well, we have heterogeneous policies. That's the idea of DEAF. Whenever you're LRU friendly, you pick LRU. And that curbs a lot of the performance loss over here while keeping the performance benefits most of the time, or most of the performance benefits. And when you're doing a study, you should always do things like this. You need to look at because you're never designing for a single point, right? You should always design for, test your idea on multiple data points, multiple system design points. So you should look at number of cores, number of cache, the amount of cache that you have, ... Your idea becomes more convincing that way, basically. Okay. And you can read the paper. This is just to show you that it's important to do these things if you want to, for example, be convincing at a company and we're the proponent of this idea, right? You need to do your homework to actually show the benefits. And that's exactly why you're doing high-level simulation in your third lab. Because that high-level simulation enables you to do this kind of studies, right? So this is another study over here. What's the size of the evicted address filter, right? So there's a sweet spot over here also. Okay. Okay, there are a bunch of other things in the paper that you can take a look at once it's assigned, or you can take a look at it right now also. Okay, so let's move on to one orthogonal approach, actually, which is a different way of getting more utilization from your cache. And that's really compression. So compression is applied in many, many fields. As we know, networks, like the videos are heavily encoded, for example. I'm sure you guys have used zip, unzip, compress. I don't know what's your favorite compression mechanism today. What do people use today? I don't know. They don't use RAR files, right? RAR files. This is old stuff, actually. Surprisingly, some people still send me RAR files. Yeah. Okay, so compression is heavily used. The key question is, can we take advantage of it inside the processor also? It's actually used in some memory systems also, in the main memory. IBM Power 8 Plus, actually, or 7 Plus, one of those. They have heavy memory compression. But inside the chip, it could be very beneficial also. But inside the chip, you have very different requirements. So one motivation, there's significant redundancy in data, for example. A lot of the data looks like this, if you look at a cache. That's one example. They have this is called narrow values. Your values are narrow. And this may happen because your integer sizes, I don't know, 32 bits, but you're storing only 4 bits. You have small integers in your program, right? There are many reasons why this could happen. We're going to look at that also. But how can you exploit this redundancy? Basically, the idea is to compress the cache, compress the data blocks in the cache. It provides the effect of a larger cache without making it physically larger. Okay, basically, you get a cache miss, you hit in the L2 cache, and if it's uncompressed, you get the data and you store it. Now, if you have a compressed L2 cache, you need to decompress the data, right? And you store it uncompressed in the L1 cache. Now, we're going to look at this approach where L2 is compressed, L1 is uncompressed, and you do decompression over here. Does it make sense to compress the L1 cache? Not clear. Why? Because the latency of decompression determines how fast you can return the data, right? This is on the critical path of a cache miss. You need this to be fast decompression latency. If this is also compressed, this needs to be really fast, right? Remember, L1 caches are tightly coupled to the CPU. And a lot of the requirements are dictated by the processor's clock cycle time. If you add a decompression step over here, now you're adding more overhead, and it needs to be even lower latency. And actually, the performance of this system is very sensitive to the decompression latency. You can read the paper for more analysis. And it needs to be simple. In the hardware, you can devise anything, of course, but if you want to devise a very complicated decompression algorithm, it'll take a long time. It'll consume a lot of area, right? All of the downsides over here. So we want actually specialized compression algorithms over here. And I'll give you one idea from this paper. Part of the idea is actually used in GPUs because a lot of the data has similar characteristics. GPUs have texture caches that are actually very heavily compressed in hardware. Okay, effective. You want, of course, compression to be effective, right? You don't want it to be ineffective. Your compression ratio should be good. Okay, so let's look at some major works. There's also related work in this area. So one idea that people have developed is compress only the zeros. It turns out a lot of the values that are stored in memory are zeros for whatever reason. For one of the reasons is what we saw earlier, narrow values, right? Or pages are zeroed out and they're never used. Now, if you only compress zeros, that's a special case. Your decompression latency is really fast, of course, because you just need to detect whether something is compressed as 0. It's 1 bit, right? Every cache block can be compressed to nothing. In fact, in the tag store, you can have a bit saying the data store is not needed for this cache block because it's 0, right? So it's 1 bit. So decompression latency, basically you supply all zeros. If you have this bit set in the tag store, the complexity is low. But compression ratio is not that good because, and also it's very benchmark workload dependent. There's something called frequent value compression, which I'm not going to go into detail. But basically the idea is somehow detect the frequent values that are stored in the cache blocks. 0 is one example. All ones is another frequent value. But you can actually detect this dynamically and have a table that stores, let's say, the 10 most frequently stored values in cache blocks, and have that table as your decompressor, right? It turns out these are actually not that easy because you need to actually do comparisons. But compression ratio actually not bad over here. Better than zeros for sure. There's also frequent pattern compression. So this is actually more symbolic. You look at frequent patterns, not the values themselves. You can encode the values as patterns in this case. Okay. We're going to look at base delta immediate compression. Let's go through this relatively quickly. Let's look at these key data patterns before we go into the paper. That's for your benefit, basically, the executive summary. So 0 values, why do they happen? Initialization, sparse matrices. You have a 1 million by 1 million matrix, and you're storing only at 3 locations. Like this happens a lot in learning, for example. You're not updating all of the weights. Some of them are more updated hot. That can happen, right? Or null pointers, right? So this happens a lot. Repeated values, this is actually common in initial values or adjacent pixels, for example, in video or images. So you can have easily something like this, and also narrow values. This happens to be narrow, but it doesn't have to be narrow. This could be repeated. This could be all Fs, for example. Narrow values, small values stored in a big data type, what I've discussed earlier. This happens a lot. You get these narrow values, and essentially you're wasting storage. And other patterns, for example, pointers to the same memory region. It turns out you've allocated all these pointers to a linked list, which you represent as an array of pointers somehow. And they all happen to be allocated from a similar memory region. As a result, the top bits are similar. The bottom bits have more entropy. They change. So all of this are actually relatively common. Basically, these are some workloads that this paper studies. In a 2 megabyte L2 cache, it looks at what fraction of the cache has this kind of patterns. 0, as you see, some workloads have 100% zeros in the cache. It's interesting if these workloads do anything, right? Now, that could be the initialization phase sometimes, right? So, yeah, this all depends on your methodology also in how you figure out. But if you look over here, repeated patterns are also a lot. Other patterns are also a lot. Okay, it turns out 43 of the cache lines belong to the key patterns in this study. But there are many, many other studies that look at these patterns also. So clearly, some of them are very compressible. Some of the workloads are not so compressible. So you have a huge variance in terms of compressibility, as you would expect. Okay, so what is common across all of these? The realization in this work is that you have low dynamic range. Basically, the differences between values are significantly smaller than the values themselves. So why don't we encode only those differences? The idea is you encode a base value, and you encode the deltas from it. Let's look at this. This is a 32-byte uncompressed cache line with pointers. You encode a base value. Let's assume the first cache block, or first 4 bytes in the cache block. You could do it at the cache block level too, but let's not go into there. That may be complicated. But the first 4 bytes in the cache block, you take that as a base, and you encode all of the other, or all of the cache blocks as deltas from that base. Right? Basically, you can do that with 1 byte per block and a 4-byte base. As a result, you get only a 12-byte cache block or compressed cache line compared to 32-byte in this case. So this already gives you a huge reduction. You save 20 bytes. Right? So what are the benefits of this? One of the reasons why this is designed this way is the compression is really fast. We will see that. It's really a vector addition, right? You take the base and you add to it in a vector, all of these in parallel. Simple hardware, it's all arithmetic and comparison, but again, adds hardware. And it has good compression ratio. So can we do better? One of the problems with this idea is, what if you have mixed values like this? It looks uncompressible with a single base. But if you have 2 bases, now this becomes compressible also, right? One base could be 0 over here. One base could be whatever this is. And more cache lines can be compressed now. The downside is, how do you find these 2 bases efficiently? And you get higher overhead because you're now storing 2 bases. You're gaining maybe more compressibility, but you're storing more of these bases. So there's a study in the paper that looks at how many bases are good for the workloads that are studied. And this is the compression ratio, for the definition of the compression ratio. Basically, how many more blocks you can store. The good way of thinking about it, a 1 megabyte cache looks like a 1.5 megabyte cache, in this case, in terms of the data storage. That's one way of thinking about it. Okay, it looks like basically here, 2 bases are the best option based on the values. This is all empirical, as you can see. Why? Because as you add more bases, maybe you really gain compression ratio in the data, but you're wasting some of that by storing the 3rd base over here, right? So you add more overhead as you store more. As you can see, 16 bases are not good because you're storing 16 things. So how do you find the 2 bases efficiently? First base is the first element in the cache line. That's one way of doing it. It turns out that's not a bad heuristic. That's the base plus delta part of the idea. So it turns out 0 values are so common that it makes sense to have an implicit base of 0. And you don't have a storage overhead in this case, right? You get rid of the base storage. So that's the immediate part. So you get better compression ratio and simpler compression logic this way. That's called the idea of base delta immediate compression. 2 bases, 1 base is implicitly 0. The other base is the first non-zero element in the cache line. So there's some complexity to determine the bases. Okay, so what does this look like? This is the compression ratio that you get in the workloads with 2 bases. It turns out base delta immediate actually gives you better compression ratio because you don't need to store that second base. Here, you need to store that second base. Right? But that's not always true. As you can see, there are some workloads where you lose by not having an arbitrary base. Right? So there's more to be done in cache compression, certainly. OK, let's look at the designs over here. So this is an idea that a lot of people actually investigate in processor design. How do you do this? There are a bunch of different ways of doing this. So a decompressor is actually the beautiful part of this. This is, in the end, decompression is a vector addition, as you can see. You take the base, add it to these smaller differences, deltas, in parallel. And with base delta immediate, it's a masked vector addition, right? If the base is 0, basically, you do actually a 0 addition. But this doesn't show that. So a compressor design is usually the more hardware-intensive part when you design this. You basically need to try out different compression mechanisms. In this case, you can have an 8-byte base, 1-byte deltas, 8-byte base, 2-byte deltas, 4-byte base, 1-byte deltas. You could actually have all of those combinations. And in parallel, you check, and you can have a 0 compression. Is this cache line 0? Is this cache line consisting of all the repeated values, ... You could keep adding to this, basically. And you can have a compression flag and compressed cache line output from all those compression units. And you really need to do this in a good way. So if you take too long, for example, your latency also becomes too long. But compression is usually not on the critical path. You're filling the cache line. You can supply the decompressed data, already decompressed data, to the processor. OK, so you get a compressed cache line based on the selection. Hopefully, you get the best one of these, right? The one that leads to the smallest cache block size. OK, so this is one example of the compression unit. You can read the paper and look at the animation. But basically, it's also vectorized. It's also vectorizable. But you need to add comparators, whether things are within the 1-byte range, right? You need to detect, for example, overflow in the subtraction. If every element is within the 1-byte range, then this compressor says, oh, I can compress it. Right? Otherwise, I cannot compress it. OK, so a cache organization. We need to change the cache organization. And it turns out this is not trivial. Right? How do you actually have a compressed cache? This is an ongoing research area also. Let's look at conventional 2-way cache with 32-byte cache lines. This is the cache blocks that you use to data storage, tag storage. You have 2 ways over here, and you have 2 ways over here. And things are nice. But if you have a 4-way, in a base delta immediate cache, a compressed cache, you need to somehow point to the compressed blocks. And one way of doing that is, and you need to also have multiple cache blocks, right? You need to be able to store more than 2 cache blocks over here. So if you want to minimize the overheads to an existing cache, one way of doing this is doubling the cache tag store size. Basically, you have twice as many tags. Now you can store 4 cache blocks in the same amount of data space. So you have compression encoding bits saying, how did you compress it, so that you can decode it. And instead of looking at the data storage as 2 ways over here, now we're looking at it as segments. Right? Now the tags point to the segments. For example, this tag can say, I'm pointing to a compressed cache block, and it's compressed this way. That spans 3 of these segments over here. So it's really a 24-byte cache block that I'm pointing to over here. And you can point to 4 different cache blocks. Now this reduces overhead, but it does add, it adds overhead compared to this, but it reduces overhead compared to making the tag store and the data store completely decoupled from each other. Right? Another way of designing a compressed cache is getting rid of this abstraction and always having a single tag store and completely decoupling them from each other. But we're not going to talk about that. If you're interested, let me know. So the overhead of this is relatively low. The goal is to keep the overhead low. It turns out the overhead is about 2.3% additional hardware for a 2-megabyte cache. Of course, so the downside over here is you can store only 4 cache blocks, whereas you may actually have better compressibility, right? So if you want to store many more cache blocks, then you need to increase the tag size, which adds more overhead, number of tags. OK. So these actually give you some references. So as I said, 0-based designs are limited applicability, frequent value compression, pattern-based compression. You can look at these if you're interested. But it turns out these other designs are complicated because decompression latency is long. So decompression latency over here is, for example, 5 cycles. Here, it's 8 cycles. Maybe you have a little bit more compression ratio improvement. But those cycles, if you're not benefiting from decompression that much, these actually add dead cycles, basically, additional cycles before you can access the data. And you got to be very careful in compression because of this overhead. So base delta immediate compression was developed to minimize that overhead. You can actually get the decompressed cache line in 1 cycle. OK, let's look at the cache compression ratios very quickly. This is 0 cache. That's 0 compression, frequent value, frequent pattern. So base delta immediate is actually slightly better than the best of these. Of course, it's not as good as the paper has comparison to LZ compression, for example, Lempel-Ziv compression, which is used in a lot of systems. Compress, for example, used to use that at least. And that actually gets you to around 2x or so. But that's very expensive to implement. Because if you actually have arbitrarily compressed cache blocks, you don't have this beautiful decompression mechanism, right? Decompression becomes very serial now. If you need to figure out, so a lot of these compressors work by stuffing compressed blocks, and they have variable sizes. Here, one of the benefits is the compressed blocks have fixed sizes, right? You know exactly the size. It's 8-byte base, 1-byte blocks. So you can easily locate, you can easily decode, you can easily decompress the thing that you're looking for. Whereas the other ones are very serial decompression, which I'm not going to go into again. You can look at the paper. OK, so you can look at the paper also for this, but this is another paper that I would recommend so that you can see the methodology in presenting these results. Again, you want to vary different parameters, L2 cache size. So of course, compression works better with smaller cache sizes, right? That's the performance improvement. And this doesn't look very high because it's a single core again, right? If you have a 16 megabyte cache with a single core, you still gain significant performance improvement. And if you look at this, you get the performance of it 2x size the cache without making the size of the cache 2x. You keep the data store size the same, actually. And this is the misses per kilo instruction reduction. OK, so multi-core, clearly compression has a lot more benefit in multi-core. And you can read the paper for that. I'm not going into detail. And actually, the performance improvement are highest when you have sensitive workloads. You need to have cache-sensitive workloads and high compressible workloads running together, right? If that's the case, then you get the most benefits. And the paper has a lot more analysis about that. But I think this is probably a good time to stop. There's a lot more in the paper, and you can look at that. And that will be one of the recommended readings. And if you're more interested in compression, there's a lot more work in memory compression and GPU. Actually, GPUs, as I said, do compression, not general purpose compression. Actually, they do some sort of base delta compression in the texture caches, because if you think about pixels in a screen, they look very similar, actually. Actually, some of this data look like pixels on a screen, and they work very well with base delta compression. So GPUs are actually specialized compressors, decompressors that compress that texture cache. OK, I think we're, oh man, 1 more minute. So that's good. Any questions, the burning questions? This is a good place to stop. I'll see you tomorrow. Thanks.